Okay. Physics. Chapter 9. Chapter 8. So we get chapter 8. Good. Chapter 8 is the homework that I put in today. That's all right. Now it's got a boatload of questions in it, but I don't think it's too much work. As I have said before, as we get in further into the book, the homework, the concepts, I think, come a little easier. And the homework is not quite as challenging, in my opinion. Of course, my opinion may differ from your opinion, but I think that my opinion is shared by most people who take this class and most people who teach this class. But let's see, in chapter 8, we got all the way into 8.3, we finished 8.3. So today we're going to do collisions, which was what your lab was all about, so it'll just kind of be a little bit of a review and a little deeper delving into what you did in your lab. Were you here to do a lab today? No. Do you still have a lab to do?
Yeah, I have to.
Okay. If you want to do a lab before a class, just send me an email or call my office or something, so that I can know to be here. I'm just asking, you weren't here early today to try and do that, right? Okay, good. I hate to.
I'm just going to an after
Yeah, just give me some warning a day in advance or so, and I can be here early if you want to make up that lab time. But we did 8.1, 8.2, and 8.3 before the long weekend. So let's do a really quick overview of those, and let's move on to the collisions part. So remember, linear momentum, different than energy, but similar. It involves mass and velocity, but in the energy, there was no direction involved. You could have negative and positive energy, which indicated whether the energy was being added to the system or taken away from the system, in some cases. But with kinetic energy, for example, you couldn't have a negative energy because it would involve having a negative mass, since the velocity was squared, and that would get rid of any negatives. So kinetic energy could only be positive. Potential energy could only be negative if you chose your zero to be above your ending point. And let's see, what else? What other situations did we have negative energy? Spring energy, we could have negative potential energy, and some other ones, but it's a different thing, because now momentum, while it involves mass and velocity just like kinetic energy, it is a vector quantity. And so momentum is pointing in a particular direction. It is pointing in the direction of your velocity, for example. Now, if we're only in one dimension, then we only need to worry about positive and negative direction. If we're in two dimensions, it'll get a little more complicated, and we'll deal with that later. But momentum is certainly a quantity that is vector quantity, and with a little manipulation, we can determine that force, and the manipulation is dividing by t on both sides. They do that right down here. If you divide momentum by t and you divide mv by t, then you get this equation, delta P over T, or delta momentum, change in momentum over time equals mass times change in velocity over time, and change in velocity over time is, of course, acceleration. So you can rearrange this equation to make this one equal to force, and then force is equal to change in momentum over time, which tells us that a force causes a change in momentum. And the force, of course, is also a vector quantity. So if you apply a force in a particular direction, that force, the direction of that force will determine the direction of the change in momentum as well. And here we use the force momentum equation to calculate a racket speed or something like that, or the force of a racket on a ball or something like that in this section. But these are the two main equations that we get out of this section. Momentum vector equals mass times velocity vector. And force vector, net force vector, equals change in momentum vector, which would be momentum final minus momentum initial, over the change in time that force is acting. Up to this point, we haven't really talked about how long a force acts in time. We've talked about how long a force acts in distance, but not in time. So this is a little bit new to us. And then we moved on to the second part, which is impulse, where we learn about a new quantity, which we call the impulse, where we take that equation, that force equals momentum over time, or change in momentum over change in time. We rearrange this so we get change in momentum equals force times change in time. So a force that is applied over a certain amount of time is called an impulse. And you get the value of that impulse by multiplying the force times the time that it's applied for. So impulse is an impulse is literally a change in momentum caused by a force. And we use that equation down here to calculate change in momentum. Calculate the change in momentum for the ball bouncing off the wall, or whatever else. If it bounces off straight off, or if it bounces at 30 degrees, it turns out that the change in momentum for the ball that bounces straight off is greater than the one that bounces off at 30 degrees, because it actually changes its velocity more going straight forward to straight back than the one that's going at a 30-degree angle, which only changes one of its velocities. It only changes its velocity that is perpendicular to the wall, and not the one that is parallel to the wall. That one doesn't change. So impulse momentum. And then we moved on to the conservation momentum. And this is the big deal. The big cheese. Conservation momentum is this idea that momentum is not lost. As scientists were studying it, they discovered, or they measured, or however you want to say it, they determined that momentum is transferred back and forth between objects, but it is not lost between two objects. And that was very interesting, because they had made the determination that energy was transferred between objects and not lost, or created or destroyed is a better way of saying it. But they did find out that energy can easily be dissipated. It can leave the system very easily in a different form, in a form that's very difficult to capture. And some of those forms include things like heat and friction and sound and other things like that. Things that are difficult to contain within the system. So momentum is a little bit different than that. Momentum does not take forms that easily dissipate out of a system. So, sorry for all those things there anyway.
No, I just wanted to make sure it was okay. I could move them.
Yeah, that's fine. In fact, you can throw them in the box if you want to.
Okay. Sorry, Mike.
No worries. So, that's the idea of conservation momentum. And just like with energy, if you add up all your momentum at the beginning of a situation and add up all your momentums at the end of the situation, they should equal each other. However, you do have to be careful with momentum, because not only is the value conserved, but also the direction of the momentum is conserved. So if your original momentum in your system is forward and at 5 meters per second, kilograms meters per second, which is the unit for momentum, it's mass times velocity, so it's kilograms meters per second. Then if that's your momentum at the beginning, then that has to be your momentum at the end. Even if you have multiple momentums, they all have to add up to equal that 5 kilogram meters per second to the right. I think that's what I said to begin with.
Mr. Dale.
Yes.
So is momentum conserved even like when you factor in things like friction and resistance?
Yes.
Is that
Momentum does not transfer into friction or heat or sound or anything like that. And that's what really makes it quite unique. Energy does. Energy does get used up, you could think of it as, or it gets lost in these different forms of dissipating energies, but momentum does not. And that was the really kind of brilliant discovery of when it came to momentum, is that it is separate than energy and also conserved. So,
okay, so like if you have a moving car that has momentum and then it breaks, how does conservation of momentum apply there?
so it breaks,
and then stops.
so it uses its brakes to stop?
Yes.
Okay. So it's conservation of momentum in just a car as it's slowing down, is what you're saying. The conservation of momentum in that case is a little bit difficult to imagine, but it is there. It actually puts its momentum into the Earth's momentum.
Okay.
And now it's a momentum that's hardly noticeable and not even measurable, really.
Because it's a car compared to the entire.
Yeah, well, not only that, but there's also a car in Australia that's doing exactly the opposite thing. There's so many cars doing this, on the Earth that it doesn't really, it's not, even if you could measure it, even if the Earth was a much smaller mass, if you had the same number of people and cars on it, all those different momentum changes would kind of cancel each other out.
Okay.
Hello, Cassidy.
Hi, how are you?
I'm very well. How are you doing? So a great example of conservation of momentum is actually just the recent holiday, right? So where can you observe conservation of momentum on the 4th of July?
Fireworks.
Fireworks, right?
So it has zero momentum when it's sitting on the ground, and it still has zero momentum when it's going up because you have the gas or whatever is combusting going this way with momentum.
Yeah, so that's one way, because fireworks are launched with an expanding gas, and it's an exhaust that comes out of the back of the firework. So as the firework goes up, part of the firework, a part of the firework that was in the firework before but is leaving the firework, is going the other direction. And if you add up all the mass of the gas going down and multiply by its velocity going down, and you calculate the momentum of the gas moving down, it will equal the momentum of the firework moving up. Now, where else in the firework do you notice conservation of momentum? What happens at the top? It explodes. And for fireworks where if the center of the firework stays still during the explosion, then the firework is going to be spherical, because everywhere that there is something moving one direction, there has to be another thing moving the exact opposite direction with the same momentum, right?
So it's not going to explode just in one direction.
Some of them are designed to do that, actually. Some of them are designed to explode off in one direction, but what happens to the firework in that case? It recoils backwards to the other direction, right? So some of them are designed to do certain things, some of them are designed to do other things. So there is a conservation of momentum going on, for sure. There's even a conservation of momentum with the whirly-twirly spinning ones, but we'll talk about that in the next chapter.
What section are you on right now, Studio?
We are in section 3 right now of chapter 8. This is the end of the last section that we covered last Wednesday. So, conservation momentum principle. The total momentum as a vector is constant. So that means the magnitude and direction is a constant in anything, in the universe. If we're talking about an isolated system, then we say that the initial momentum total is equal to the final momentum total, and that's pretty much the same idea. But we talk about this in terms of an isolated system so we can get an equation out. And the isolated system is defined as one where there is no net external force acting on the system. So forces from outside the system are not affecting it in any way.
Even if a force outside the system acted on it, the momentum would still be conserved because that.
Overall momentum would be conserved, yes. Even if a force acts from outside the system, the momentum of the universe remains the same. So, here is our system of interest, our isolated system. The rocket. It has the first stage launcher on the bottom of it, and then it has this cone on the top, and at the top of its movement here somewhere, the second stage blows off or shoots off the top of this rocket, and the bottom of the rocket goes down while the top of the rocket goes up, thus conserving momentum. If the bottom of this rocket has a mass that is twice as much as the top of the rocket, what is the comparable velocity relative to each other of the bottom and the top of the rocket?
It's going to have to go twice as fast, right?
Which one?
The top.
If the top is half as big as the bottom, or the bottom is twice as big as the top, then the top one has to go twice as fast, right? And we're going back to this idea of momentum equaling mass times velocity. You know, if they have to have the same momentum splitting off relative to each other, relative to the center of mass, I guess is a better way to say that, then the top one is going to have it twice as big of a velocity to have the same momentum as the bottom, right? So this turns out to be an extremely important thing in many physics and engineering questions. This also actually answers a lot of questions in subatomic physics, actually in all physics. I mean, the people who are studying the expansion of the universe, which is about the biggest thing you can study, it is the biggest thing you can study. The biggest thing you can study in the universe is the universe. So if you're studying the expansion of the universe, they're using conservation momentum to determine where the center of the universe is, because they measure all the stars around us are moving away from us all the time, and we're moving away from them. And the ones that are furthest from us are moving the fastest, relatively speaking, and the ones that are closest to us are moving the slowest. But they can use all that data and use a conservation momentum equation to determine where the center of mass of the universe was, which was where we presume the Big Bang happened, right? So it's kind of interesting how they use it in the biggest physics, but they also use it in the smallest physics. It's in the smallest physics, they're using it to look at small things like quarks. A quark is one of the smaller particles out there. An electron is even smaller still, but there are several particles that we consider fundamental particles, which are particles that cannot be split into smaller things. And to study these small particles, we actually throw them at each other. That's the only way to really study them. Light is much bigger than these particles, for example. So you can't use lasers or anything really to study these things. You have to use other tiny little particles. So they use these particles they throw them at each other and they watch them react with each other and recoil off of each other. And what they're really doing is they're watching their change in momentum. So if you throw a bunch of electrons at some material and you know what their momentum is to start and then you measure what their momentum is to finish, you can actually calculate something about the particle that was sitting still that got hit. Because you'll have the mass of both particles and the velocity of one. So initial momentum equals final momentum. The equation, the only thing you don't know is the final velocity of the final particle. Or maybe the final mass of the final particle, if you know the velocity of the final particle. But anyway, that's one of the things that's used quite a lot, actually. It's not as straightforward as we use it at all. Because it turns out that at very, very small levels in nature, things do not behave in a continuous fashion like we work in. We work in a continuous universe at our level of the universe, where we can say, well, I have a sandwich, I can cut it in half, or I can cut it in thirds, or I can cut it in eighths, or I can cut it any size I want. But in the quantum world, or in the subatomic world, where you have these subatomic particles like protons and electrons and quarks and other things, those things can only behave in very certain ways. They can only eat a single sandwich, and they have to eat it all at once, for example. They can only walk, they can only move in steps that are certain sizes, and they can't even exist in between the steps. So that'd be like having steps in your house that you walk up to go upstairs, but you never exist in between each step. You just go from step to step to step, and there's no existence in time and space in between the steps.
You just tell it.
Well, That's actually exactly what I'm talking about. Teleportation is something that was just recently achieved, and
With what? Like I know electrons.
with atoms, it's on subatomic particles and atoms.
Because I know that like part of the problem with some of the like subatomic models that showed like electrons was that like it didn't work, so you had to have.
Teleportation is not what people think it is exactly, but it is what people think it is exactly. That's a great answer, isn't it? Teleportation is not necessarily the movement of matter. It's not necessarily the movement of matter through space. It's the movement of information through space and time.
It's not necessarily moving the matter, just moving the organization.
You can think of it that way. Yes. So what they did is they actually had an atom on Earth at a laboratory and an atom on another laboratory on another part of the Earth, and there was a satellite in between them, and they entangled these two particles so that they were behaving exactly the same way. So that essentially, if you did something to this one would react instantaneously without any time.
Really?
And that's what it is. It's a reaction of particles because they're entangled, and the entanglement process is a little bit beyond our. It's kind of like being having some kind of I don't know what it's like. It's being connected. They're connected. They're connected in a well we call them a quantum state. They have the same quantum state, so you could consider them almost to be the same atom. It's pretty much what we're talking about here. So you have two atoms that are behaving exactly in sync. And if you do one to one thing, if you do something to one, the other one, it doesn't even react. It's not even a reaction. The other one, it's like the other one is being affected at the same exact time. So that's what teleportation technically is. But anyway, the point is that all of those studies at the subatomic level are all done with these conservation laws, and momentum is among the greatest conservation laws. It is one of the ones that is held up forever, and it works at every level of physics. And if we ever do create a theory of everything, I'll bet you that conservation momentum will be at the heart of it. We haven't really figured out the theory of everything yet, but we're working on it. So now let's do some collisions, because collisions are really where we see this interchange of momentums, this trading back and forth of momentums and this conservation of momentums. And we've already talked about some collisions. We did the collision lab last week, right? So we talked about the fact that we have two kinds of collisions, an elastic collision and an inelastic collision. And it's important to know the difference. In an elastic collision, the internal kinetic energy of the system of interest is conserved. And we call it elastic because it's bouncy. You know, it's got a perfect bounce in between the two things that are colliding. There's nothing crushed, there's nothing deformed, nothing sticks together. They perfectly bounce off of each other, and the internal kinetic energy is conserved. So you can say that, you know, initial kinetic energy, add all the initial kinetic energies together in the system together, and then they have to equal all the final kinetic energies in the system added together. But the other thing that's interesting is the momentum also has to be conserved. So that gives you another equation to work with. Your total of momentum has to equal the same number before and after the collision. So you end up with two equations that you can work with to solve this system of variables or unknowns that you're going to have. Remember that these two only work if there's a net force of zero, and so the conservation momentum, the net external force on the system has to be zero. And for conservation of kinetic energy, there cannot be any forces that are non-conservative. Non-conservative forces include things like friction. So friction is a non-conservative force. So how do we use these two equations in a collision? Well, you've done it in the lab. Let's do it really quick in the book. We have velocities of two objects following an elastic collision. So these are the velocities after the collision. We have velocity 1 equals 4 meters per second, velocity 2 equals 0 meters per second, and we have mass 1 is 5.5 kilograms, mass 2 is 3.5 kilograms. So we know everything that happens after the collision, and we want to know what their velocities were before the collision.
mass is constant, so that's
The masses are going to stay constant, and these final velocities we don't know. So we need to find out the two initial velocities, and we just happen to have two equations. The initial momentums have to equal the final momentums. These are your initial momentums, the P1 prime and the P2 prime. And your final momentum, remember that velocity 2 finally is 0. So your final P2 is 0, so they don't include it on the left side over here. And then also energy is conserved because it is a elastic collision. And that means your final kinetic energy, they said these are the finals. Yeah, this is, calculate the velocities of the two objects. Well, these must be the initial velocities. And we're calculating, it doesn't really matter, either way you'll get the same answer. But anyway, yeah, these are the initial velocities, not the final velocities. You'd get the same exact answer, just in the opposite direction if you did it the other way. But it looks like they're using the prime for the final, which is what I thought they were doing before, which confused me a little bit. So their prime is the final velocities, and their unprimed is the initials. So their first equation is that the initial velocity, the initial momentum of block 1 is m1v1, but the initial momentum of block 2 is 0 because the velocity 2 is equal to 0 to begin with. And then these v1 prime and v2 primes are your final velocities. So that's one equation. The second equation is the kinetic energy equation. 1 half m1v1 squared is going to be the kinetic energy of the first block, and 1 half m2v2 squared would be the kinetic energy of the second block, but because v2 is 0, it becomes 0. So these equations get a little bit simplified, and that's nice. And what they're going to do here is they're going to solve for v2 prime in this equation right here, the momentum equation. They solve for the v2 prime, and they get this, m1 over m2 times v1 minus v1 prime. And then they plug this equation into the kinetic energy equation for v2 prime over here, which means they're going to square it, which is going to be messy. But either way, you're going to have to do something. So anyway, they plug that in there, and they get this big messy equation to solve for v1 prime. When they do that, when they solve for v1 prime, then they get 4 meters per second. Now, whenever you're solving collision equations, you're very unlikely to get exact answers. It's possible that this is an exact answer, but it's also possible that that's not quite exact. It's an approximation or a rounding or something. So just be aware of that. It's very common. Just because you have all these squared things in here and you end up taking square roots and it's messy. But then they plug that v1 prime, they get v1 prime is 4 meters per second and negative 3 meters per second. And remember that you can get negative velocities, right? So you got to be careful of that. Let's see. So in this case, they throw out the 4 meters per second. Can you figure out why they throw out the 4 meters per second from these initial conditions? What they're saying is that V1 was initially 4 meters per second, and their first solution was 4 meters per second for V1 prime.
So it can't be the same.
Yeah, they're saying that if it's going to collide with something else, it's going to change its velocity. So it's not going to stay the same velocity.
So what we just found out is the fact that after it collided, the mass 1 is moving in the other direction.
Yeah, so it's got to be the other one. It's got to be the negative 3. So what they do is they plug in that negative 3 into the equation that they solved for V2 prime, and then they get 1 meter per second for V2 prime. And then you can plug those back into both equations and find out that they both work just fine. That one makes more sense. So to draw a picture of this, let's see. Let me put this into share screen mode. So if we're going to draw a picture of this, it would look like this. We have block 1, and it's moving at 4 meters per second this way to begin with. And it has mass 1. And then block 2 to begin with is not moving at all, has a 0 velocity. And that's before, but after, here's the after situation. After we have M1, block 1, moving with a speed of, actually, it's actually moving backwards now with a speed of -3 meters per second, right? According to our equation. And block 2, now moving forward with a speed of 1 meter per second. And that we can understand that. That makes sense. This block comes in here and hits this one and pushes it forward a little bit and gets bounced back a lot. That tells us that mass 2 must be much bigger than mass 1, and when we go back here and check that, it is. You know, it's 7 times bigger. So we would expect a velocity that's quite a bit smaller with mass 2. And that is our conservation of momentum in an elastic collision, along with the conservation of kinetic energy in an elastic collision. Now, is this true if both blocks, let's see, in your lab that you did last week, you had both blocks or both cars sitting still. Was conservation of momentum still true there in that case? They're sitting still, and then they exploded apart. Was the momentum conserved? Yeah. However, was kinetic energy conserved in those situations? It was not. Because when they're sitting still next to each other, they have a kinetic energy of 0. And when they're going apart, they both have a kinetic energy that is positive, because it's 1/2 mv squared. So kinetic energies cannot be negative. They can't cancel each other out. Momentums can cancel each other out. The conservation momentum can happen in that situation, but the conservation of kinetic energy cannot. And that's what takes us to the different type of collision that we call an inelastic collision. In specific, we're going to talk about the perfectly inelastic collision. Most collisions are partially inelastic. In other words, they're not perfectly perfectly elastic, but they're also not perfectly inelastic. Most of them are kind of a mix of the two. But an inelastic collision is one where you either start or finish up. You either start as one object stuck together, or you end as one object stuck together and moving at the same velocity. So with the two cars sitting next to each other, you could consider them as one object not moving. But you could also have two blobs of clay or something, or two cars on the freeway that hit each other and get stuck together, which happens a lot on the freeway. They kind of wrinkle together, and then they're stuck and they slide together off the road or whatever. That's also a perfectly inelastic collision. Well, not perfectly inelastic because there's still friction on the road, but anyway. So here is a definition for a perfectly inelastic collision: a collision in which the objects stick together. And if it's going to be perfectly inelastic, you have to say a collision with which the objects stick together and there are no external forces acting on the objects. So you'd have to include that to make it perfectly inelastic. But in the case of a perfectly inelastic collision, we still conserve momentum, and within the system, the momentum within the system is still conserved, but the kinetic energy is not conserved. So let's take a look at this example. We have our puck and our goalie example. Let's go back to our screen share here. There we go. So here is the goalie catching the puck. So we have a puck that's, we have an ice hockey goalie that's 70 kilograms. And we like this situation because even when the goalie's on his knee pads on the ice, there's not that much friction between him and the ice. So we're going to assume there's no friction. The goalie is going to catch a 0.150 kilogram hockey puck. And the hockey puck is going to have a velocity of 35 meters per second. And the goalie, of course, has a velocity of 0 to begin with. And we want to know how much kinetic energy is lost during the collision. So we have to find the recoil velocity and then find the lost kinetic energy. So, first of all, to find the recoil velocity, we're going to have to use conservation of momentum because that's the collision. Puck hits goalie, goalie, and puck move backwards. But that means that our masses are combined in the end. In other words, mass 1 and mass 2 at the end of the situation are combined together. So what we do, instead of having our initial momentums added together equal our final momentums added together, We have our initial momentums. The M1V1 is the goalie, the M2V2 is the puck, or vice versa. I don't know which way they do it. But in the end, we don't have M1V1, M1V2 separate. Afterwards, in the prime side, we add the two masses together to make one mass of puck plus mass of goalie. And then we, instead of having a V1 prime and a V2 prime, we just have V prime because they're moving together because he's holding the puck. So they have the same velocity. So this is the new equation for a perfectly inelastic collision. What's great about this equation?
One velocity.
That's right. We just got rid of one of our unknowns, right? So we've made our life a little easier. We can solve for that single unknown, and we can plug in all these things that we know already. Mass 1 over mass 1 plus mass 2, we know all the masses, and the initial velocity of the puck, right? Because the initial velocity of the player was 0, we also got rid of one of the initial momentums because it was 0. But anyway, we can solve for the final velocity of puck and player, and this equation only works if one of the objects to begin with is at rest. So you can use this equation in every situation where you have two objects colliding, where one of them is starting at rest, and the other one's hitting it. And it's perfectly inelastic collision. But anyway, we do that, we throw this in here, we throw all the masses and the initial velocity of the puck in here, we get 7.48 times 10 to the minus 2 meters per second for the final velocity of the puck and the ice hockey player. Which makes,
Very much.
well, it's 7 centimeters per second. So that's, 7 centimeters is a few inches, 3 inches or so. So 3 inches per second. And that's about what you see with an ice hockey goalie. If they get a puck hit at them really hard, it might push them back a couple inches. And that's what we're seeing here. And the direction is determined by the sign of that momentum, because we're only in one dimension. Positive is one direction, negative is another direction, and the positive 35 meters per second was in the direction of towards the goalie, and that 7 at the end, where did it go? Here we go. At the end, that 7 centimeters is in that same direction because it's still positive. If you plug in all your numbers correctly, all your velocity with the correct signs, you will get a number out that tells you the direction. Now, we know the final velocity of puck and player, and we know the initial velocity of the puck and the player separately. Player being 0, the puck being 35 meters per second. We can calculate the kinetic energy initially and the kinetic energy finally and take a difference. So here's the initial kinetic energy. 0.150 kilograms times 35 meters per second squared, times 1/2. Remember, the velocity gets squared in kinetic energy. So that 35 meters per second is huge. What is 35 squared? Anybody know? It's like 1,000, right? That's a big number squared when you square that.
1225.
So, what's that?
1225.
Yeah. So, it's a big number. And the 7 centimeters squared, that's a tiny number, right? It's not going to be very big for the final, even though you have the mass of the puck and the player, the velocity squared is a tiny little number. So it's gonna be a big difference in kinetic energy. We take our final kinetic energy and our initial kinetic energy, take the difference, 0.196, 91.9, you get a 91.7 joule kinetic energy difference. It's like a 90% something loss, 99% loss of kinetic energy or something like that. And where does that kinetic energy go? How is that kinetic energy lost?
Right?
Yeah, it deforms the pads, makes a loud sound, it hurts their hand. If you catch a 35 meter per second hockey puck, glove or not, it's going to hurt. That thing is unless you catch it exactly in the pocket of your glove, and even if you catch it in the pocket, it might break the glove at 35 meters per second. That thing is moving.
How fast does the hockey puck normally go?
Well, hockey pucks can go up to about 35 meters per second is like 60 miles an hour or something like that. But hockey pucks can go up to about 100 miles an hour on a stop shot. So it's like a baseball.
Except you pass in hockey and baseball,
Well, yeah, they do at least the goalie has some pads, some good pads. So, I mean, it's been hockey pucks have been known to kill goalies if they hit them in the face with the old face pads, the ones that didn't have the screen and the helmet on them, the ones that were just the plastic thing, like the horror movies use. Those things were not very safe, and it's been known to. I mean, it would just break right through and break, just crack their skull. And it can happen. So that makes sense. That's a lot of kinetic energy going on. But that kinetic energy of the puck is really high, and that's why it's so dangerous. The kinetic energy was completely lost in the sound and the deformation and everything else, the squishing of the pads, so the goalie doesn't have hardly any kinetic energy to end with. A goalie, no matter how massive they are, moving at 7 centimeters per second is not very dangerous. It doesn't matter what it is. It can be an iceberg moving at 7 centimeters per second. It's not going to hurt you. But a hockey puck with that, with that energy that it started with, is extremely dangerous. Even a very, very small object like a 22 round out of a rifle is extremely dangerous because it's moving so fast. The movement is the thing that makes it dangerous. And that's actually an interesting, another interesting application of momentum and kinetic energy. If you talk about this in California, you get yelled at in class by people, but in Nebraska it's not as big a deal. Military science is a very important science that physicists play a huge role in, and engineers. But a lot of people didn't like it when the United States switched to the 7.62 round that they use now in their in the M16 or the AR-14 or whatever it's called.
I think the standard ones, and it starts with that. I have a military friend
The M1 rifle. Oh, the original, the actual designation of the rifle. Yeah. I don't know what it is either, but it's some mixture of letters and numbers. But anyway, it's the rifle that has been handed down from the M16 of Korean and Vietnam War. But anyway, the rifle they used before that was a the 30 caliber M1 rifle, which had a great big bullet, a great big casing on it that would shoot this huge, it's like a cannonball coming out of this thing. It was heavy, and it was, if you got hit by this thing, it just stopped you in your tracks. That's what the people said. You got to have a big bullet to stop people in their tracks. And about the same time that the United States was moving over to this new rifle, the M16, the Russians were moving over to their version of the new kind of rifle, which was the AK-47 and the AK-74. But the AK-47 and the M16, the AK-47 is a little older. It was designed in 47 and introduced in 49 or something like this. But this is all science. The Russians' idea, their thought was that you need a big bullet, and it needs to pack a big punch because it's a big bullet with a big charge of gunpowder behind it. And sure, that it can do. It makes a big hole. That's what it does. However, the rounds are really heavy because it's got a big chunk of lead on the front. It's got a big casing full of powder, and that thing's made of brass or steel or something, and it's heavy. And you can only carry, if you're carrying an AK-47 around, you have to not only carry a heavy gun that is shooting a heavy bullet, but you have to carry heavy bullets, and you can only carry about 200 of them at most. If you're not carrying anything else, you can carry 200 rounds, which is, I think, 6 or 7 magazines of those things, and any more than that, your average. What's that? Yeah, 200 rounds is not much. You'd have to reload 2 or 3 times a day in a heavy battle. And the M16 has a round that weighs half as much. I mean, that's significant. You can carry twice as much ammunition, and the rifle is lighter.
Which would give you more ammunition or other things.
And then that's exactly what the United States was thinking. We want a rifle that we can carry twice as much ammunition. And a lot of people said that's a bad mistake because the M16 doesn't make as big a hole. You're not going to kill people. But the difference is the M16 round, being so much lighter, can be shot so much faster. So it has a much, much higher velocity. And what happens to the velocity in the kinetic energy equation? It's squared, right? You square the velocity. So if you can go twice as fast with your bullet, you're going 4 times as much energy, which means 4 times as much damage. And they've done a lot of tests on this, and what they discovered is that all that energy turns into a lot of damage internally. It makes a small hole, but inside the body, it turns and it twists and it rolls and it does all kinds of internal damage. It becomes a much more efficient and effective weapon. Now, it seems a little cold-hearted and everything to apply science to killing people, but that's actually the #1 use of science in the history of man, is killing things and people. Animals to begin with, and people not long after that. So it's not like it's a new thing that we've discovered in the 20th century to use our minds to kill animals and people and plants and other things. But it was sound science. It was not an accident. This was done this way on purpose. They knew that the kinetic energy was the thing that does the killing, not the momentum. So the kinetic energy being a velocity squared thing, it's the velocity that matters. And I mean the 22 bullet and the 223 bullet, which is the one that they use in the M16, are almost the same exact width, almost the same exact diameter. You can shoot a 22 bullet. The 22s are just tiny little things, they're like pebbles, but almost the same bullet. The 223 round is longer so that it's more stable, but it's a very tiny little bullet.
So how does 22 do that? Just one. More powerful?
It's not as stable, so it can't go as far, and you can't aim it very. It could do a lot of damage if you could get it to shoot that far, but it's not very stable. A longer bullet is more stable traveling through the air with all the air friction. So that's the reason they made it longer, and it made it a little heavier, which doesn't hurt either. So, well, it does hurt, but not the person. But anyway, that's a bit of science, and there's a lot of science like that in things that we don't think about. One of the things we'll learn about in the next, at some point, is some of the science that goes into railroad. There's so much science that's in railroading. You'll be surprised how much, and it's not new stuff like with computers and things that they use today. It's not that stuff. It's old science that was on the railroads from the very beginning of steam railroads and everything like this. So, let's do this one here. We have final velocity of 2 carts that collide. They're going to collide inelastically. So the pictured in which figure are we looking at here? Oh, it's this figure. Here's our carts now. So these carts are shaped in this funny shape because they're air track carts, which I have one of them, but I don't ever use it hardly. But they're low friction carts, so there's no external forces. Net force external is 0, and it's got this spring in between them. The spring is going to help these carts to bounce off each other very, very elastically. Apparently, say it inelastically. Why are they using a spring then?
It's inelastic.
Yeah, that's what I was thinking. This is the figure they're talking about. So I don't know why they put the spring in here. That's kind of dumb. But they should have put a big blob of clay on the front, so when this one hit this one, it's stuck together. But anyway, we have 2 masses, 2 carts, and then they're going to stick together afterwards. And they want to know... oh, I see what they're saying. They're saying that the spring is compressed originally. And then when they hit together, it releases its potential energy, converts it into internal kinetic energy, and pushes the other cart, I guess. Okay, so this is kind of weird. Let's see if we can figure out what they're talking about. Let's draw a picture and see if we can figure it out. So what I think they're saying here is that we start out with this one cart that has this compressed spring. I'm just going to draw it as a really compressed thing here. And then at some point this hits the second cart. So this is what we've got to begin with, just this thing over here on the left. And then it hits the second cart, and that's the inelastic collision. They're stuck together and the spring has not released. So this is the inelastic collision right here. But then I think what they're saying is that separately afterwards, they spring apart so that this spring releases and shoots them apart so that the one card on the left, which we'll call cart 1, this is 1 and this is 1. This is 2. So the card on the left ends up shooting off this way. This one starts off going this way. And then we have our collision crash right here, right? This is our collision. And then after the spring releases, we have this released spring that's now all stretched out. And this one is going to supposedly move backwards now, while the other one moves forward. We don't actually know if it's going to move backwards. So that's an important thing. We're not sure about this backwards direction. We'll find out in the equations. But it might be backwards. But this second block is certainly going to be moving forward, right? There's no doubt about that. Velocity 2 prime is definitely going to be forward. Velocity 2 initial is 0. And then we have a velocity 1 initial over here somewhere, and a velocity 1 final over here. So I think that's what they're talking about. So we have an inelastic collision here, and then this one is another inelastic collision where they start together and move apart. I think that's what they're talking about. Now let's go back and see if that matches what they actually do. So, momentum of the conservation of momentum. We have, let's see, they're using this one. So this is not an inelastic collision here because the masses aren't combined on the final, right?
So we would just treat it like an elastic collision, right?
Let's see, they're solving this for V2. I think what they meant to say is that the original collision is elastic. But as they collide, we add some energy in with the spring. So this would be the velocity 2 final after that collision. But then there's some internal kinetic energy. Let's see. So this is the internal kinetic energy before the collision. I don't get it. Oh, they both have they both have an initial velocity. So the initial velocities, this is the initial velocity before the collision. These are the velocities after the collision. Okay, I know what they're saying now. I know what they're doing now. Sorry to confuse you. They are doing it just like it is shown up here, but what they're saying is the spring makes this not a perfectly inelastic collision, but an inelastic collision because the spring adds kinetic energy to the system in the middle. So this is an example of an inelastic collision that is not perfectly inelastic. So they're both moving towards each other, but this spring causes them, the spring that is compacted to begin with stretches out as they hit, and it adds kinetic energy to both blocks. So both blocks have more kinetic energy than they should at the end, and that makes it an inelastic collision as well. So that's a little bit confusing, but that is what's going on. So that's why they don't combine them at the end, because they're not stuck together. They don't combine the masses finally. And then initially they both have a velocity, and finally they both have a velocity, and then they just use this equation, which is always true, really. So you can use it anytime you want. You just have to realize that in situations of perfect inelastic collisions, you will have the same velocity for velocity 1 and 2 prime, and masses will be added together. In this case, they're not, so you just solve it, you get that final velocity for the second block, and then you use that final velocity for the second block. Well, they've actually already given us the final velocity for the first block, so we're good. So we find the velocity of the second block, and then we use that final velocity for the second block with all the other velocities and masses that we know to calculate the kinetic energies to begin and the kinetic energies to end. And then you just take the difference and you get 5.46 joules. So because that's a positive energy right there, a positive 5.46 joules, taking the final minus the initial, that tells us that energy was added to the system. And it was added by the spring in the middle. We had some potential energy stored up in the compressed spring that was released into the collision valve. Now that is probably the hardest part of dealing with these problems that have momentums that are conserved and energies that are conserved, is just keeping track of directions of momentums, keeping tracks of energies going in and out. Remember, energies going into a system are positive for the system, or negative if they're going out of the system or leaving the system. Keeping those things straight are the biggest challenges in these problems. The equations are pretty straightforward, and everything else is just solving some algebra. So. But this is where it gets really fun. Two-dimensional conservation of momentum. The classic ones we like to use in physics are billiard balls and hockey pucks because they're round of shape. Makes the geometry a little easier. But in a situation like this, where you have a billiard ball coming on and hitting this second billiard ball, the purple one that was the first one that was moving, the second one was sitting still, the first one was moving. And then the first one shoots up here to the left, and the second one shoots down to the right. You see that all the time in pool. That's what happens if you hit the ball slightly off center or way off center. Right? You get this one ball moving one direction, one ball moving the other direction. But answer this question for me. Let's make this a quiz for today. Everybody get a piece of paper and a pencil. Does everybody have paper and pencil? Faculty have paper and pencil? Okay. Everybody get a paper and pencil. Write your name and date. Are you awake there, Cole? We're going to have a quiz, Cole. Grab a paper and pencil. Okay, using words only, no equations or mathematics, I want you to explain to me, 20 words or less, or you could maybe even just justify to me the conservation of momentum of this system. You're starting off with a billiard ball moving to the right, the purple ball, mass 1, and a billiard ball that is sitting still. The purple ball hits the orange ball slightly off center. The purple ball goes up to the right. The orange ball goes down to the right. How is momentum conserved? And I want you to talk about it in 2 sentences of 10 words or less each. One sentence is going to describe the conservation of momentum in the y direction, or the up and down direction. And the other one is going to talk about the conservation of momentum in the left-right direction, or the x direction. Okay? I want you to explain, using a very simple phrase, a very simple sentence, why conservation of momentum is conserved in each of those dimensions. You don't have to give me any details or anything else, just figure out the most important thing that describes or explains or justifies why momentum would be conserved. Why do I say in 10 words or less? Because I really want you to whittle this down to the most important concepts, the most important words you need to say. It doesn't even have to be like a complete sentence like your English teacher would expect. But I want you to write down some kind of phrase or something that really explains why it's conserved in the x direction, why it's conserved in the y direction. The thing to think about is what is the initial momentum in the y direction? And what is the final momentum in the y direction? What is the initial momentum in the x direction? What is the final momentum in the x direction? And what is momentum anyway? Right? Remember that momentum is mass times the velocity vector. I'll give you a couple minutes. I'm going to get a drink of water, and then we'll be back to discuss. Okay, does anybody need more time? Raise your hand if you need more time. Got one. Okay. I can give you another minute. All right, does anybody want to share? Want to share? What do you want to share, X or Y?
Whichever one you want.
Pick one.
Y.
Okay, this is an explanation for conservation of momentum in the Y direction. Give to us.
Okay, in the y direction, momentums offset each other.
In the Y directions, the momentums offset each other. In other words, they cancel each other out?
Yes.
Okay, that's a good statement. Why is that a good statement? Anybody else want to add to that? What's the momentum in the Y direction to begin with?
0.
0, right? Because there was no movement in the Y direction, there cannot be any momentum in the Y direction. So the momentum of this system at the beginning was 0 in the Y direction. It only had momentum in the X direction. So in the final part of this system, it also has to be 0, but they're both moving in the Y direction, so they have to be moving in opposite directions in order for them to cancel out. Now they're also going to be moving at opposite speeds depending on if their masses are the same or not. So if their masses are the same, their Y direction speeds also have to be the same, don't they? Yes. So that's another thing that's quite important. And that leads to a very interesting situation that you'll learn about as you do your homework. But it'll help you with your pool game too. Does anybody know the angle between the two balls that are moving here?
45.
No, not quite. Good guess. It's actually 90 every time. So if these two balls have the same mass and the same diameter, and there's no friction or low friction, and they hit off center like this, where one ball is sitting still and the other one is moving, the angle between them will always be 90 degrees. The angle between their final paths, and you can bet that pool players take advantage of that. That's one of the keys to playing pool well, is understanding how that angle is going to work. There are only two exceptions to that rule. What are the two exceptions? I'll give you a clue. If you hit the ball exactly head on, what happens? One ball stops and the other one goes straight forward, right? What's the other exception? If you miss. If you miss, the original ball just keeps going, and the one that was sitting still just sits there, right? So those are the only two exceptions to that rule. But this is two-dimensional conservation momentum. You have to split the momentum into an x momentum conservation, which means you have a velocity in the x direction for each of these, which means you're going to be using components again. We're back to using vectors. I told you that we would come back to it a little bit, and we are coming back to it. But you have to do it in the x direction, and then you have to do it in the y direction, and then it has to be conserved in both directions. So the conservation of momentum in the x direction looks like m1 v1x, m2 v2x, m1 v1 prime x, m2 v2 prime x, and then some of them are 0 at the beginning, or some of them are 0 at the end, or whatever, and then you can solve that equation. You're going to end up with some cosines and some sines and so on and so forth because of the angles that the balls end up moving. And the same thing in the y direction. You'll do the same thing in the y direction, and you'll have conservation momentum along the y-axis. So, this is a great example of what we do in subatomic physics and even in interstellar physics and intergalactic physics. We're often trying to figure out what's going on inside of a dark room. Now, sometimes the dark room is space. We don't know what's out there. We want to know what's out there. But sometimes the dark room is like an atom. For the longest time, the atom itself was a dark room. We had no idea what it was made of. We had all these different theories about what it was made of, but we didn't have a clue what it was made of. Does anybody know how they figured out what it was made of? How do we figure out that the atom actually has a nucleus with these tightly packed masses in it with electrons going around the outside?
Because they would bounce off of it.
That's right. They actually did an experiment. There was an experiment done by a guy named Ernst Rutherford, and he earned the first Nobel Prize in chemistry, not in physics. He deserved the one in physics, but they gave him the one in chemistry because he made a really funny joke. You want to hear the joke? Ernst Rutherford was well known for being ornery, and he was at a big conference with all these scientists, and many of these scientists were very famous and had a lot of influence in Europe. And Ernst Rutherford went to this conference and he said, physics is the only true science, all the rest is just stamp collecting. But there were a lot of chemists there that really took offense at that. They thought that, and he was, and most of these people were chemists, and so he was certainly taking a shot at chemistry. He didn't really like chemistry very much. And so he was taking this big shot at them, and so when some of these people were on the Nobel Prize board later on, it was I think in the same year actually, later on in the same year when they were deciding who was going to get the Nobel Prize, the first Nobel Prize, we're talking this was the first time it was ever given out. They were deciding who would get it and what, in the Peace Prize or the Literature Prize, and then it came down to physics and chemistry, and they decided not to give it to him in physics. They decided, because he wanted it in physics, of course, but they gave it to him in chemistry because he discovered that atoms have a nucleus. And the way he did this was he took a piece of gold foil, which is just gold hammered super thin. It's so thin, gold can be hammered so thin that it's almost see-through. So there's only a few atoms of thickness to it. So he hammered it out super thin, and then he started shooting alpha particles at it. At the time, they called them alpha particles because they didn't know what they were. They just knew that they came out of uranium. But we now know that they're helium nucleus, so they're 2 protons and 2 neutrons stuck together. And he was shooting these alpha particles at the gold foil, and his thought was, if I fire these alpha particles, I know these alpha particles have a positive charge to them, and I know that atoms have negative charges in them because they discovered that using electricity, they could pull electrons out of atoms, and they called them electrons, but they didn't really know what they were. So he said, if I can shoot these positive particles in that are really massive, and he knew that they were heavy compared to electrons, he says, if I can fire these into the gold, then they will go straight through, just like bullets going through cake. But there's these little negatively charged raisins in them. They're just these tiny things inside the cake. If my alpha particle comes near them, it will get attracted to them a little bit, but it won't do much to them. It'll just turn them a little bit. And that's exactly what he saw. He saw these particles going straight through and just hammering through this gold foil. But every once in a while, one was turned off course a little bit. So he got a little bit of diversion. But then one of his students came in and measured behind the gold foil, the same side that he was shooting from. And he discovered that some of these alpha particles were actually coming straight back. And there was no way to describe that using the model that they were talking about, this cake with the raisins in it. They called it the plum pudding model because they were English. It's a cake that has little bits of raisins in it. But the point is that the only thing that could have enough oomph to push that alpha particle back would have to be something extremely massive, much more massive than the alpha particle. But they had no room for that in their model, so they said, well, we have to change our model. We have to assume that the atom has something that is extremely massive, but because we only get a few coming back to us, about 1 out of every 1,000, then that massive thing that's in the atom has to be 1,000th the size of the atom. So it has to be 1,000 times smaller than the atom, and the rest of the atom has to be just empty space. And that's how we discovered what the atom is made of, how the atom is constructed. It's mostly empty space with a part of it that is extremely dense mass, and the electrons just kind of float around out there somewhere, right? So that is the black room of the atom, the room that we can't really see into. But this experiment is another darkroom experiment. So they got this 0.250 kilogram object that is being slid on a friction into a dark room, on a friction on the surface into a dark room. So it's like standing outside this room, turning all the lights off and shutting all the shades, and then throwing tennis balls into the room to figure out what the room is made of. See how the tennis balls come out, right? That's what most of subatomic science is about, and it's also most of what interstellar science is about. The science is in between all the science that we can see with our eyes, cars crashing into each other, balls falling, and throwing things out of the Eiffel Tower, the Leaning Tower piece. That stuff is easy to measure. But the stuff that you can't see, that's where it gets challenging. So you have to start throwing tennis balls into dark rooms and see what comes out, right? So we're sliding this object in on this friction surface, and then it strikes an initially stationary object that has a mass of 0.4 kilograms, and the 2.5 kilogram object emerges from the room at an angle of 45 degrees with at an angle of 45 degrees with its incoming direction. And so the speed of the 0.250 kilogram object is initially 2 meters per second and is 1.5 meters per second after the collision. I'm going to calculate the magnitude and direction of the velocity of the second object. So I definitely want to draw a picture for this one. Let's make our dark room. So here's our dark room, and here's our object inside the dark room, and here's our object outside the dark room. And outside the dark room, we shoot this object in, and then it comes out like this, right? Goes in at 2 meters per second, comes out with this 45-degree angle, and 1.5 meters per second. And this one inside is initially at rest, so velocity initial of 2 is 0, but then it goes off at some direction. We don't know what direction it goes off at, but it's going to go off at some direction with some velocity 2 prime that we don't know either. Right? And we're going to assume that it's going to go off at some angle. We don't know what that angle is going to be, so we'll just call it theta. But how are we going to do this? Well, remember that we split two-dimensional problems into two problems. We have an x side of the problem, and we have a y side of the problem. On the x side of this problem, we have an x velocity for each thing here. So this one right here is equal to the velocity of, this is ball 1, this is ball 2. So this is velocity 1, but it's also all in the x direction. I'm going to call this my x direction, and this my y direction. They're probably going to the right to begin with. It's my guess, so I'm actually going to switch this around really quick. I'm going to call this velocity 1, and my x direction is going to be to the left, because that's probably what they're doing, is my guess. So that's going to be my x direction, positive x direction. So this is actually velocity 1x, because it is moving in the x direction, and it is the x component. So velocity 1x is just going to equal 2 meters per second. Right? Velocity 1y is what? What's the initial velocity in the y direction? 0. Right. How about velocity 2x initially? Well, it's not going anywhere, so it's 0, right? And velocity 2y, we don't know, right? So put that as a question mark. Sorry, velocity 2y initially is 0. We do know that. That's initial. Finally, we don't know. We don't know. So those are our initial velocities. So we can actually calculate our initial momentum, because it's all tied up in this initial thing here, right? But final velocity 1 in the x direction is a different deal, right? Because it has two components. It has a y component, which is going to be downward in this case. It has an x component, which is going to be over this way in this case. So it's going to be the x component where this 45-degree angle is next to the x direction, so that's going to be cosine. So velocity 1x prime is going to be velocity 1 prime cosine 45 degrees. And it's going to be, I know that it's going to be negative, so I'm going to put a negative sign on it.
How do we know it's going to be negative?
Because it comes back out the same place it went in. They did say that. I know that the x direction velocity will be negative. And my velocity 1 y is going to equal velocity 1, this is prime, velocity 1 prime sine theta, sine 45 degrees, right? Oh, we still got to do our velocity. So velocity 2x in the x direction prime is going to be velocity 2 prime, and it's going to be the cosine of the angle theta, which we don't know. And velocity 2y prime is going to be velocity 2 prime sine theta. Now this is kind of getting crazy, because now we have all kinds of things. We don't know what theta is. We don't know what velocity 2 prime is. But we do know velocity 1 prime. We know the final velocity coming out is 1.5 meters per second. So that's this right here. The 1.5 meters per second goes right there. right? So we do know that. We also know the velocity 1. We know the initial velocity, so that's good. But in the end, we're going to use all these velocities with these masses to create an equation, two equations. We're going to create an equation for conservation momentum in the x direction and an equation for conservation momentum in the y direction. So conservation momentum in the x direction is going to be velocity 1x, which is the 2 meters per second here, times mass 1. And then velocity 2x, which is 0, so that just goes away. And then for the other side of the equation, it's going to be velocity 1 prime x, which is this whole thing here, times mass 1, plus velocity 2 prime x, which is all this right here. Then we have an equation that has two things we don't know, velocity 2 prime and cosine and theta, right, in this part. Everything else we know. We do the same thing with our y's over here. We add our velocity 1, y, it's going to be 0 on the left-hand side. We add these two together on the right-hand side. And we're going to have another equation that has two things we don't know, velocity 2 prime and sine theta. And I highly recommend that I'm going to show, we're going to see that the best way to do this, anytime you end up with two equations that have the same angle in them that you don't know, one with the sine, one with the cosine, you put them together and solve for the sine over the cosine, which is the tangent, and then use that to get your answer. And so let's go back to the book and see them do that. But this is the setup. You split it into coefficients, and then you find your velocities in each direction initially and finally, and then you set up your conservation momentum in both x and in y. So you get two equations, one for x, one for y. But when you plug in your components, you end up just having velocities themselves, not the velocities in x or y. You have the velocities and the angles, and then you can solve for both of them. So back to the Batcave, Batman.
Is it asking us to find anything for the second object? Yeah.
I'm sorry?
Is it asking us to find anything for the second object or not?
Yeah. It wants to know magnitude and direction of the 4 kilogram object, which is the second object.
And you do that right when you find the x and y velocities
Yep.
for the first.
Mm-hmm. So, here, well, I'm glad I did all that because they don't do any of that. They just tell you to do it. Well, here they kind of show, they show you the equations, what the equations look like in the end. This is what they look like in the end. And then they take a ratio of the two equations where you get the sine of one on one side over the cosine of the other here. And that gives you the tangent of theta. And that's the tangent of theta 2. So that's the tangent of the angle we don't know. Theta 1 is the angle we do know, which is the 45 degrees. Or, yeah, 45 degrees. And then you just plug in all those numbers and you get the tangent of theta 2 is equal to negative 1.129. Take the inverse tangent of that number, and you get an angle of 312 degrees. Then you can plug in that angle into your equation anywhere you like to solve for whatever else you want. And in this case, they plug in to solve the second velocity.
For the just where you're drawing this, once you found that angle, the second angle thing, like, is it 312 degrees?
So it's 312 degrees from wherever you measured your very first angle. So let me show you that really quick. So my very first angle I measured down from the x-axis, so this should technically be negative 45 degrees. And I showed that when I put it in, and I put the negative right here. Because the negative of the cosine of a negative angle is equal to the negative of a cosine of the angle. So I took the negative all the way through and put it out front here. So technically it should be negative 45 degrees. Or I could have shown the angle coming out from up here and called it positive 45. It doesn't matter either way. But just make sure that you're consistent with it. So if I measured downward from here and called that negative, then upward from here would be positive. And 312 would take you all the way around to here, somewhere, right?
So wouldn't that mean that, like, you slid the first object this way, it comes out this way, the other one comes out this way?
So what that would mean but their case, they measured it differently. So So they're measuring it differently. Let's go see how they're measuring it. I don't know how they're measuring it. Their angles are defined as positive in the counterclockwise direction, and let's see, and they're going to the right. So here's their picture. They're going to the right. So their first object comes in this direction. Oh, wait a second. They drew it very differently than I did. I drew it as coming back out in the same way. They drew it as going out this direction. So they interpreted that problem very differently. But the problem is still, solving the problem is still the same thing. However you solve it, draw the picture the way you interpret it. And because the way I interpret it coming back out, and that's fine.
So as long as the way you interpret it and the way you solve it match up, it's still the way.
That's correct.
Okay.
That is correct. I should have looked at that picture. I didn't see the image before we started. So in this case, they're coming straight in and it's glancing off this direction. And then the other one is moving off at some angle. We don't know. It turns out it moves out at the 312. Since the 45 is measured up from here, the 312 is all the way down here somewhere. So it's going to go downward to the right.
Okay, that would make sense.
But you can never rule out anything, really, right? It's a good idea to always do the math and then check your measurements, kind of like the student of Ernst Rutherford. It's kind of a funny joke because the student of Ernst Rutherford didn't get the Nobel Prize, but he's the one that discovered what happened. So that happened a lot back then. So anyway, the key to two-dimensional conservation momentum. Split the problem, draw a great picture. That's always an important thing. But split the problem into x momentums and y momentums and create a x momentum conservation momentum equation and a y momentum conservation momentum equation. From those two equations, you should be able to solve, by putting them into a ratio, you should be able to solve for the angle, the final angle, or the initial angle if they give you the final angle. What?
Using tangent, right?
That's right. Solving for the tangent of the second angle, you should be able to solve that. And then you go back and use that angle to solve for the final velocity. And that is something that is used again and again and again and again in physics. The dark room experiment, as we call it. There's actually a great, I think I have one here. There's a great game. But it's like they have this little, it's like a little pinball machine that you can shoot things into a little dark box and try to guess what's in the box by how the marbles go in and come out. It's kind of interesting. So that is the end of our collisions. The last part of this chapter is rocket propulsion. So now, after you've done this, you can officially say that you are rocket scientists.
But it's not rocket science.
This is rocket science right here. This is certainly rocket science.
Can I get going?
What's that?
Can I get going? I got a place I gotta be.
Yeah. So, how do we calculate the acceleration of something that has more than one force? Well, you have to add the forces together, and then those are equal to the acceleration times the mass, right? In the case of a rocket, what are the two forces acting on a rocket? The
Gravity.
propulsion up and gravity down, right, Cassidy? Cassidy said gravity down. We have propulsion up and gravity down, two forces. If you solve the equation that is propulsion minus gravity, the force of gravity on a rocket, this is the equation that you end up with. And it looks a little bit strange because it has this velocity in it and this mass in it and this change in mass and change in time, but it does all work. The change in mass over the change in time times the, let's see, the change in mass times change in time, times velocity is actually the impulse from the jet engine. And then this minus g with this m attached to it, if you multiplied everything by m, you would get the weight or the pulling down from gravity.
What's the V sub E?
The VE is the velocity of the exhaust. So the velocity of the exhaust times delta M over delta T is actually the impulse or the change in momentum from the rocket engine, is what it is. But this is, and this is not exact, but it's a good approximation. The reason it's not exact is because rocket engines do not expel their exhaust with the same velocity all the time for their entire burn. And they don't behave as simply as this equation assumes. But it's still a pretty good approximation. So this equation is the acceleration of a rocket equation. We can use that. And this is what it looks like. We have a rocket moving upward. We have the exhaust moving downward. And the force is the force of the reaction from the rocket pushing upward and the weight pulling downward, right? The really interesting thing is that the rocket is changing its mass as it goes. Why is that?
Because it's combusting, expelling.
That's right, it's burning fuel, and that burnt fuel is getting shot out the back in the form of this plasma fireworks display, and that has mass. All the mass of the fuel that burns is going out the back. So it is changing its mass all the time. So you do have to know that delta M factor. So let's calculate the mass of the Saturn V rocket. Anybody know what the Saturn V rocket was?
One of the Apollos.
The Apollo missions. What's interesting about the Saturn V rocket?
The biggest one ever built.
The biggest one we ever built.
So the ones that launched the space shuttle were smaller,
Oh yes, quite a bit.
more efficient, or was Apollo bigger? Or?
The ones that launched the space shuttle are more efficient, but they also didn't have to go as high. You know, to get a rocket to the moon, you had to really get that thing moving.
Yeah.
And so, but the ones that launched the space shuttle they're quite efficient, but they're also very messy because they're solid fuel rockets, so they just blow all kinds of nasty contaminants in the air. The one that launched the Apollo missions, the Saturn V, burned hydrogen and oxygen. What happens when you burn hydrogen and oxygen?
You are.
Yeah, you get mostly water in the end. If it's a perfectly efficient burn, you get just water, vapor, but not so with the solid fuel rockets. They're like fireworks. So they're just a big chemical rocket that burns all kinds of nasty stuff into the atmosphere.
So do you think the only time we might ever build a bigger rocket is if we ever try to do like a manned mission to Mars?
Yeah, well, I don't think we'll necessarily need to build a bigger rocket.
That might be comparable in size.
But what they've done actually is the Russians built a much more efficient rocket that burns hydrogen and oxygen. They built it actually a long time ago. We just didn't know about it because of the Cold War. And they built it a long time ago, and then they just put it in cold storage. I mean, they literally just boxed it up and put it in big warehouses, and then it was never seen again until recently. Recently, when they started dismantling the nuclear arsenals of both countries over the past 20 years or so, some European and American engineers discovered these old rockets hanging around in Russia, and the Russians said, "Oh yeah, I forgot about that project," and so they started building them again. That's why Russia takes everything into space now instead of the United States, because they're much cleaner and much more efficient. So it's really quite interesting. They're great stories and great documentaries about that right now. But let's look at the Saturn V just because it's cool. The Saturn V rocket, here's a comparison. The Saturn V the Ares 5, which is what we use for putting huge payloads into space now, the Ares 1, and the Space Shuttle. Space Shuttle's kind of itty-bitty compared to these guys.
Yeah.
This is what we had to do to replace the Space Shuttle, though. The Space Shuttle, these are the same rockets here on the side of the Ares 5. But the Space Shuttle had this big tank that was underneath it, which is essentially this part right here. And this part up here is the back of the Space Shuttle. So this can carry bigger payloads, slightly bigger payloads than the Space Shuttle. But
So essentially from the space shuttle to the Ares 5, it's just like you stuck the space shuttle on.
it's like sticking the Space Shuttle on top, yeah, pretty much, and putting no people in the Space Shuttle, and a much smaller computer. The Space Shuttle was essentially just a big plane that held a huge computer. The computer in there was monstrously big. It was a huge iron core computer, so it was just really heavy and really clunky, but it was the only thing that could handle the launch and not just get rattled to pieces. It can handle all the problems with being launched and being in space and still be very reliable. So
I think I heard one time that the computers that they use for the Apollo missions, like the little things that you have like the talking gift cards, that's more computing power.
oh
than
yeah,
that or
oh
something.
yeah. Everything has more power than those computers. Here's a great diagram of this, the Saturn V rocket. The really interesting thing about the Saturn V rocket is they can't build it anymore. They don't even have the plans for it anymore. And they were lost somehow. It was essentially a work in progress. Every time they built a new one, they were improving it. And the engineers knew everything about it, but it was the same engineers from beginning to end. And they did a terrible job of kind of preserving all of and it was not just one company either of engineers. It was engineers from like 10 different companies. So it was kind of crazy. But anyway, it has 3 stages to it. And the first stage was just to get them off the ground and get them into orbit. The second stage was to speed them up. And the third stage was to shoot them to the moon. So it's kind of an intense beast. It was really something to see when they launched, from what I hear, from what people say. So they still have one. They still have one in Florida. Let's see if they show a picture of it.
I've seen it.
Have you seen it, Cassidy?
Yeah.
Is it pretty
I
impressive?
did that. It was amazing.
Yeah, it's in one of the hangars. Is it standing up or laying down? I can't remember.
It's laying down.
Oh, here it is. Is this the one in Houston?
That one, that says it's from Houston.
Did you see the one in
That's not
Houston?
the right one.
Did you see the one in
No,
Houston
I
or the one in...
saw Florida.
You saw the one in Florida. So the one in Florida is not a replica. It's an actual Saturn V. And it was, if I remember correctly, they were going to use it.
Oh, go down.
Yeah.
Go slow. Down.
So if we have an actual one lying around, why not just reverse engineer?
It would be a beast to reverse engineer this sucker.
Going down.
It's here somewhere.
Is that it?
Oh, okay.
This one right here?
Cursor down. No, well, maybe, but down.
Down here?
Right. That I have like the exact same picture.
Okay.
I can't.
Yeah, so there it is right there. That is just a beast. So yeah, it's on my bucket list to go down to Florida and see that down there in the hangar. But anyway, super huge beast. It took them like I think it took them a week to get it out to the platform every time they launched one of these things. But I believe that the last one they were going to launch when the program was canceled by politicians, and so they just never did anything with it, just left it there. But
Well, if I remember correctly, Apollo 17 was the last one to land on the moon, but they were still in Apollo 18 mission.
There was a mission, but it never launched. I don't believe.
No, I could swear there was an Apollo 18 mission. It was supposed to be like the end of the space race. So like
I
we
don't know.
launched someone with like an Apollo capsule. They launched a Soyuz capsule and they docked in space and like shared it.
They made it.
They may have.
Not that obviously.
Let's see, let's go here. I don't remember if Apollo 18 actually was launched. Yeah, I don't think it
Wait,
was.
click on that. 'Cause it said the official lead unnumbered Apollo spacecraft.
See, this is the Apollo 18 I know. Is the They Might Be Giants out here. Yeah, it's just
The Apollo Soyuz test rocket.
unnumbered. Oh yeah, so it's just unnumbered, and they called it. Some people call it Apollo 18. So yeah, I suppose the Soyuz was the first space station. So I guess they did launch it up there. So yeah, I guess they.
It was Russian made.
It was Russian, but it crashed in Australia, and the guy whose property ended up not paid thousands of dollars by the Russian Navy for random trinkets.
Random trinkets, huh?
Well, random trinkets is the way the official description of it is.
Anyway, that's certainly one of the biggest rockets ever launched. And it's kind of interesting because the United States rockets all had this very distinctive look, very similar to the Saturn V, very cylindrical, just very much like this. All the rockets looked very much like this. The Russian rockets looked nothing like that. And their design was so incredibly different. The really interesting thing, though, is that they were both designed by Germans. So each one of them was designed by Germans, not by Russians. But the Russian rockets all had this kind of triangular shape to them and had multiple rockets down here instead of just this one big cylinder thing. And it was just a very interesting difference in design. But the Russians got into space first. They were first ones to have a reliable rocket, and they were certainly the ones that built the most efficient ones. Why didn't they get to the moon? Probably because they ran out of money. They just couldn't keep up. The United States had so much more money and so many more resources than Russia. So it was kind of a race of money. So anyway, back to physics of rockets. Your free body diagram for rocket just has the force from the rocket upward and then the weight downward. And if we want to calculate the acceleration, we need to know those two things in the end. Well, we also need to know the mass of the rocket and how the mass of the rocket is changing. For the Saturn V, the mass at liftoff was 2.8 times 10 to the 6 kilograms. And it burned fuel at a rate of 1.4 times 10 to the 4 kilograms per second. So that is your delta M right there. So the exhaust velocity, which is the V sub E, 2.4 times 10 to the 3 meters per second. We calculate its initial acceleration from that. Plug all the numbers in and get 2.2 meters per second squared. Now let's check to see if that makes sense. Well, we got to do a famous one. Apollo 11 or Apollo 13. Let's do Apollo 11. So what's important about Apollo 11? That's the one where they landed on the moon, right? So 2.2 meters per second. Let's see if we believe it. So what you're seeing right there is actually ignition. That's not actually the launch. That's the lighter that lights the
They
candle.
have to get warmed up before they actually can.
Well, this thing does not light itself. It is actually lit externally. It's like a lighter on a. It's like using a lighter on a.
I'm assuming not by a person. That's some
No.
sort of system.
No, it's definitely done mechanically, not by a person. But now you see all that fire coming down in. That's when they've turned on their fuel. Now they've ignited the actual engine. All that plasma gets sucked down in and ignites the actual engine. And you can see this is obviously in slow motion. Now, another really interesting thing about these is if you're looking closely, you see things falling off of this. What's falling off of it?
Ice.
Yeah, it's actually ice. Because the tank is full of liquid oxygen. You see ice coming down up here too. Now it's all falling down from above. The liquid oxygen is like 200 degrees below zero. And so the water in the air in Florida down there would just condense on the side of the rocket in like inches of ice. And then when they lit it and it started to vibrate, all that ice would break off and fall down. And it would just evaporate almost immediately in some cases. So you get this huge cloud around it of water vapor, and you can see the cloud starting to build up here. Now you can see the restrictors falling off the rocket. Those are the things that hold it up. And it's going to let the rocket go. 2 meters per second, can you believe that? It doesn't move that fast. This is slow motion. Or is it? Yeah, this is slightly slow motion. It's not extreme slow motion. But it is still slight slow motion. Holy mackerel.
I'm just imagining if the job description was, yeah, get under the rocket, light it, and then run while you can.
Anybody have a match? Back then, everybody had matches or a lighter in their pocket because everybody smoked. My neighbor who's like in his 80s has taken to smoking these like foot-long stogies in his backyard. His doctor told him to stop smoking like 30 years ago, but he said, but that was a long time ago. And he told me to stop smoking cigarettes, not cigars. Kind of funny. Anyway, let's see if we can find another one that actually shows it in real speed here. Let's get a real speed rocket launch for 7.5. Apollo 11. CBS will have it in real speed. All right. Where's Lance Armstrong? Or not Lance Armstrong.
Jail.
Yeah, well, he's not quite in jail. But
Not on the Tour de France.
3 minutes to go. 2 minutes to go. Here we go. 2.5, 25, 24, 18, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 3, 2, 1, and here we go. 2 meters per second, can you believe it?
Yeah.
Yeah. But it accelerates. Because immediately after it's going 2 meters per second, it's lost weight, right? But it still has the same thrust. So it's losing weight every second, every fraction of a second, and so it accelerates more and more and more and more and more and more and more the longer it's going. And now, contrary to popular belief, these rockets didn't just blast straight up. They went up for a little while, but then they started pitching. You can notice already that it's already turning over. And by the time it would clear the upper cloud layers, which often were around, it would be almost horizontal. You can see it's pitching pretty radically at this point.
Why would that be?
Because to get into orbit, you actually have to be going a certain speed parallel to the Earth, remember? So it's not how high you get, it's how fast you're going parallel to the Earth. So you have to get this tangential velocity that's extremely fast. So then,
what we're trying to do at first is just get into orbit, and then that's what the first stage is for. The second stage launches you out of orbit towards the moon.
that's correct. So the second stage actually gets you going in a faster orbit. So you go faster and faster and faster, and you get further and further away from the Earth. And then the third stage shoots you off there.
Yeah, a really good camera back when you can see it.
Yeah, it's a telescope camera at this point. Then you should be able to see the first stage burn out, and the second stage take off here soon. So here it comes. Just, can you see it? We're barely going to see it, I think, here. There it goes. So that was the second stage, and the first stage drops. See the separate stages now? First stage burnout, second stage light right. Oh, it's already lit.
I guess that's the fall in the first stage.
Yep.
Were they high enough at that point that it's going to burn up? Or
No, it fell into the ocean. And I can't remember if they retrieved it or not. Good. What's that? Well, because it's so stinking heavy, it's so big. No, they weren't reusable. I don't think they ever retrieved them. So
If I remember correctly, like the rocket boosters for shuttle.
oh yeah, those are reusable.
The fuel tank burns up after the big orange red thing. The fuel
Yeah.
tank will burn up, but the rest is all reusable.
So looks like they recovered some things. I don't know. Oh, here we go. They actually just let them fall down to the bottom of the ocean, but they retrieved them later just for museum pieces. Yeah, they just let them fall into the ocean and sink. So pretty crazy stuff. All right, let's go back to our enough fun and games.
So real quick, in our formula, the change in mass and the change in time is all represented as
So delta M over delta T is this number. This whole
just the
thing
fuel burn rate.
is the fuel burn rate. So this delta M over delta T is 1.4 times 10 to the 4 kilograms per second. And they plug it in right there. And they calculate that 2.2 meters per second. Okay. So here's another equation that they give us without explanation. It comes from some calculus stuff. But this one will tell us the final velocity of a one-stage rocket that is initially at rest will equal the initial velocity v sub e, or sorry, the exhaust velocity v sub e times the natural log of the initial mass over the mass of the rocket at rest. No, the mass of the rocket residual. So the initial mass is the total mass divided by the mass of the rocket without any fuel or whatever is left.
So what it's saying is like the final velocity after the first stage.
After the first stage. Yep.
Okay.
After the first stage is complete burnout, that's the final velocity of a rocket. And you can use this equation in a couple of different ways. One of the ways they show us right here is that you can actually solve for the mass of the rocket. So this equation here, if you solve for the mass of the rocket, you end up taking the natural log here and raising it to the exponential, the natural exponential. So if you raise this side to the natural exponential, you get mass. You don't have to remember any of this, but you get the initial mass over the mass expended, or the residual mass equals this e to the 4.48, and then you solve for the mass of the rocket without the fuel in it, and you get the initial mass divided by 88. So only 1/88th of the mass is left after the fuel is gone.
Is that for any rocket?
It's for any single stage rocket that, let's see, any single it's for a single stage rocket that will get you into orbit. The escape velocity is 11.2 times 10 to the 3 meters per second. So if you want to get into orbit, you have to have a rocket where 88% of your mass is fuel. Kind of crazy, huh? Or sorry, 98.9% of the rocket is fuel. Now you see why it's so stinking expensive to get into space and so difficult. Well, it's because it's all fuel. You only get 1% of payload and plus rocket, right? The rocket plus anything you carry up into space is only 1% of what you need to get there. And that's why it's so expensive to get into space. Because 98%, 99% of it is expendable. It's stuff that's going to be gone. And this is one of the reasons they wanted to invent different ways to get into space. For example, using rail guns and having space platforms in space. You just slowly take things up to space and then launch from there. Elevators they're working on right now, maglev space elevators that will just carry things up into space. All these crazy things that will eventually become realities. So anyway. So let's look at this one. I don't think I've ever played with this one before. There we go. Where is it? Why won't it open? Open with Java non-true. Oh well, won't open. Okay, so let's go look at the homework for a little bit here and see what we got in store for you. You'll be happy to know that I didn't give you lots of two-dimensional problems. I think I gave maybe one or two. Let's see here. I can't even find one. I know that I gave you at least one.
I haven't seen one. It's towards the bottom.
Well, if I didn't give you one, I gotta find one to give you guys.
I saw one because you have pictures of cars.
It's here somewhere. Okay, yeah. If you've seen it, I'll trust you. But most of these problems are single dimensional, so that you're not having to worry about doing the whole X and Y thing, but I do want you to have some experience with it.
Which one was the one with the car that you just had?
With the parachute?
Yeah.
I don't know.
I was looking at that one. I was talking about the impulse.
Yep. So remember that impulse is the force that changes momentum. So it's a force times the time. The time of the force that the force is applied times the force that is applied. And so therefore it is also a vector. Impulse is a vector. It's a change in momentum.
It's number 11.
So impulse is.
Oh, there we go, yeah.
Impulse is a force times the time.
Here's your two-dimensional problem, number 11. Two cars crash each other. So this is a perfect one if you want to be a highway patrolman, right? Or highway patrolwoman, however you want to call it. Oh, here's another one. Here's the billiard ball problem. So I gave you two. But everything else is in one dimension, so I've been nice to you guys. Even though I give you 30 problems, these one-dimensional problems aren't a big deal. Now, however, I found this problem and I thought, well, maybe we should do the classic egg drop. Who's done an egg drop experiment? You've all done it? Have you done one, Cassidy?
I think so.
Think so? What were your rules in your egg drop contest? You did it at a camp? What were the rules in yours, Packer?
We had to use the stuff provided with to make an egg survive a 10-foot drop.
So did you put the egg inside of stuff or did you drop it onto something?
Oh, we put the egg inside the stuff.
Okay. Same with you guys?
Ours was, if you've been up to the Halsey 4-H camp, we were on the second story, and
Yeah.
the first story was probably about as tall as.
That's the same as well. No, more like, in our EA.
Okay.
I went to the.
But did you do something to the egg or did you drop it onto something?
Most of us did something to the egg.
Okay.
There was one team that, because the idea was like to spend the least, because you had to purchase materials to save your egg, and so the idea was to spend the least amount of money to make your egg survive. And there was one team that was like, well, we're going to guess that most of you aren't going to have your egg survive, so we're not going to buy any materials. We're just going to drop it off so that we will save the most amount of money.
Why not just spend a little money on water and fuel and boil it?
No, it wasn't the same thing. It was like sending food to Africa or something like that.
So I was thinking maybe we should do an egg drop contest while we're in Broken Bow next week, just for fun. But anyway, the point is that to do this one, what you do is to do the one that I am most familiar with. Well, the one I did last. I've done several egg drop contests. I did one when I was in junior high school off of a 4-story, off the top of a gymnasium essentially, and that one you could do anything to it. So we built a parachute and all this stuff, and of course it survived. Then the second one I did was in high school. We dropped it from 10 feet, but the only thing we could build was a 1 centimeter platform to catch it. It would be 1 centimeter thick. And if your egg survived, then you won. Our egg survived. We dropped it twice, and the second time it got a crack in it, but it didn't break. It didn't break the membrane. It just got a hairline crack in it.
What did you make the platform out of?
We made it out of Play-Doh, actually. The only other team that did as well as we did, they made theirs out of bread dough, just uncooked bread dough essentially. But we made ours out of Play-Doh. And then the most extreme one I ever did, we were at a picnic at BYU as a graduate student or undergrad, I can't remember. But they did it off the top of the nursing building, which was 17 stories tall. And you could only use stuff that was provided at the picnic. So you had paper plates and napkins, and they provided some tape and just anything that was on the picnic table. And that one was impressive. The coolest one what's that?
Did you make it?
Yeah.
What did you use for it?
We used impeller design. You weren't allowed to build parachutes, but you were allowed to arrest the motion. We just couldn't build a parachute. So we built a reverse propeller that absorbed like a little helicopter, kind of like the oak, the maple seeds that have the little.
How the helicopter.
Yeah, that's what we did, and it survived. But one group just stuck theirs. They cut open a 2-liter bottle, filled it with water, and put their egg inside, and taped it all together with the water inside. And they were guessing that would stop it. My goodness, that whole thing exploded, including the egg. It was like just eggy water. It was done.
The water might be able to stop the egg, but
Yeah, but actually what happened is that there was a concussive force from, it actually created a vacuum in the water that ended up collapsing and crushing the egg. Because they tried to take into account the acceleration that happens inside of that. But anyway, very interesting. So maybe I'll bring some eggs.
Mr. Daly.
Yeah.
Some of these first ones, like on number 2, it's asking how much force you can do.
Yep.
I wasn't quite sure how to go about solving that.
So remember that if we go back to the beginning of this chapter, and you kind of missed the review of it, so it's probably not very fresh in your mind, but remember in section 8.2, we have this equation that we solved to get the change in momentum equal to the force times the change in time. So if you know how it changes momentum and you know how much time it took, you can calculate the force.
So when it's talking about a car that's driving so fast, it weighs this much, it's going this fast, and it's stopping this amount of time,
Yeah,
a change in momentum would be, you'd figure out the momentum initially, and then the final momentum is going to be 0, because
Yep.
it's not moving. That makes sense.
Yep.
On part 2 of that, it asks the 75-kilogram passengers in the car, or whatever however much they weigh. Is it asking how much time it takes, or how much force it needs the car and the passenger, or
just the passenger.
So if I launch the person,
Well, it's just the passenger, they have a different mass. So it's going to take,
so it's saying if I just launch this person, like without a car, how long is it
Yeah.
going to take them?
so
to stop?
their change in momentum is different because their mass is different.
Okay, so that means that basically the car's not there.
Yeah,
Okay.
and that's very important to determine if you can survive an accident. This is how they determine how fast cars are allowed to go on freeways. Because now most cars have airbags. If you're on a freeway going 75 miles an hour, you can survive that crash if you have an airbag and if you contact it correctly and you're wearing your seatbelt. And that's how they calculate how fast you can go. That's how they calculate that change in momentum. Because the airbag increases the time of stopping the human inside the car. If you don't have airbags, I would not recommend going 75 miles an hour on the freeway. I wouldn't recommend it if you don't have airbags for everyone in the car. In fact, so if you don't have side airbags and airbags in the back seat and everything else, I wouldn't recommend going 75 on the freeways. I would recommend going at least 5 miles below the speed limit because that's what they're designed for.
So if I'm on a bus on a school trip, should
Well, buses on school trips don't go 75 usually.
yeah, more like 65? maybe?
65 to 70 usually.
What's
So,
the chances of survivability in that situation?
well, the great thing about school buses is that they have so much mass that they don't change momentum in a very short time very often, right? They usually slide a long way and slow down over a long period of time.
So it's not a sudden change, which is where
Yeah.
the injury would.
Same thing with most, semi drivers. They don't usually get injured in their wreck unless they turn over. But they don't usually get injured because they usually push whatever they hit for 10 seconds down the road.
Because they wouldn't.
Yeah, they just have so much momentum. So
Have you ever, I would take a guess and say, have you ever seen any of the Fast and Furious movies?
I have not.
Oh my god. There's a part where they jump into this valley and land in the water and we're like, no.
Well, in the second one, there's a part where they're like all racing to get to this one place, and one of you have like the two main characters, and then one of the other guys who's competing to be one of the drivers. His car gets shoved sideways, like underneath the trailer,
Yeah.
and And so, but he gets pushed along for a while before finally the trailer just goes over the car.
Yeah,
But,
that can happen.
You know that moment you talked about how your real physics theory when you're watching a movie, you go, that can't happen. Obviously,
Bad physics.
Independence Day was on yesterday, and the part where they shoot the alien in the lab, they shoot it with like handguns, and the alien just goes flying. That's
Maybe use really small mass. Yeah, that's one of the interesting interesting implications of conservation of momentum is that if a person shoots a bullet, they're going to get pushed back as much as the person who gets shot by the bullet, right?
so if I can secure my stance properly and not move at all except with my arm,
Yeah.
that would happen to that.
Well, and you don't even have to secure your stance with a handgun. There's not a handgun in the world that's going to knock you over. You know, there just isn't. The Desert Eagle, whatever people call it, it's really just a 44 Magnum. It's not any more powerful than any other gun, and so it's it'll knock your hands back, but it's not going to knock you over unless you're like 40 pounds.
Well, I just remember at a Boy Scout camp I went to, I was at the time also dual registered in the adventure crew, which meant that I could go shoot some handguns that they had there. And there's one, I can't remember what, it was a
I've shot a 50 caliber.
7 something Magnum,
Yeah,
and they nicknamed it Bertha.
yeah.
And apparently it was a really powerful kick or something.
Yeah. And it depends on how you load it. I mean, if you load it really heavy so that it goes super fast, then yeah. Pistol bullets aren't very reliable at very high speeds, so people don't shoot them at very high speeds usually. But I know I've shot a 50 caliber muzzle loader pistol. And didn't make me fall backwards at all. It was loud. It had a good kick to it, but I think I've shot a 45. I don't think I've ever shot a 44, but I've shot a 45, and no big deal. They're not that big a deal. I mean, you could make one push you back a little bit, but nothing's going to make you put a 50 caliber machine gun can be shot by a person. You know.
Not even a tripod.
Yeah, you can hold a 50 caliber Browning and fire it if you can pick it up. Because I mean, it's the gun itself is so heavy that any momentum it has to push you and the gun back, right? Yeah, that's one of the reasons that powerful guns are heavy. It's for that reason. A friend of mine who is a bona fide, actual qualified sniper in the military, he has a sniper rifle that he built himself, and the thing weighs. What does that weigh, Packer? 20 pounds? 22 pounds?
Probably about 20 pounds.
Yeah, it's a beast. The barrel is an inch thick on both sides. I mean, it's like 2 inches diameter. It's a monstrous barrel. I think it's like this big around all the way down. But he can shoot anything with that. And he also has an eighth of an ounce trigger on it. So he has to be very steady gun. I can't even shoot it because I can't touch the trigger without it going off. But he just lays his finger on this eighth of an ounce trigger and just fires, and he can hit something at 1,000 yards. So he can hit something small at 1,000 yards, like 3-inch targets. So, but it's the momentum is very mass dependent. So if you have something that's going to impart a lot of momentum, put it in a very heavy gun, so the gun can't push you backward. So the recoil won't be huge. If you have a really light rifle and a big round, it'll hurt. But most guns that are designed for shooting heavy things, like shotguns, are usually heavy. Usually made of a heavy hardwood or a heavy resin, so that it doesn't hurt your shoulder. And if it's not made of something heavy, they put a big fat rubber thing on the back to absorb some of that. So,
Mr. Daly, real quick question.
yes,
On number 20.
number 20.
I got the actual number correct.
Okay.
It said I had the unit wrong, even though I used the same unit I did in the previous problem.
So what's the unit you used?
Kilograms times meters per second. kg star m/s.
Okay. I don't know why that would be wrong.
The correct
But-
answer is a negative answer. Does that make any difference?
No, it shouldn't. Huh. Kilograms, meters per second. I don't know why that's wrong. Kilograms times meters per second. Well, let's go look at it. Got to so I've got to preserve everybody's privacy here. Okay, so chapter 8. What number was it again? Yeah, I did that on purpose. What number was that again?
Number 20.
20. 20, 20, 20. 20. Okay. They just want you to use their math entry system on that one.
I want you to do what?
I'll show you just a second here. Hold on. Okay. So number 20, if you click in the units here and go to the little yellow arrow, then you can do kilograms. Then go times, and then do this, meters per second, and I think it'll give it to you.
Okay.
Nope, still won't. I don't know, I'll have to check that one. I'll
Okay.
check the code on that one and see if it's coded goofy. Send me an email though, so I remember.
Okay. I'll send you a message.
Yeah, that's perfect. Okay, does anybody else have any other particular questions about problems in the homework? Number 2. Okay, so initial momentum, final momentum is your change in momentum, right? Or final momentum minus initial momentum, right? What's your final momentum? 0. What's your initial momentum? 2,600 times 21 meters per second, right? We're considering the initial velocity to be the positive direction. So there's a sign involved here as well. If you're going one direction and that's the positive direction, what direction is the force that's going to stop you? Backward. Did you consider that? So it's going to be a negative force. So the force will end up being negative in this case. And then you use the impulse momentum. What's that?
Okay, yeah. It says consider the initial velocity of the car to be positive.
That's correct.
So the force out of car in the opposite direction.
That's correct. So your force is going to end up being negative because the initial direction of the car is positive. So this is what's happening. Let me draw it on the whiteboard here. Whiteboard. And let's clear it. So here's our car. Nice car. It's going this way. That's our initial velocity, whatever it is. Our final velocity is 0 because we're going to stop, and we're going to stop in 2.2 seconds, did it say? Delta t equals 2.2 seconds. Right? Our final velocity is 0. So our initial velocity is whatever it is. So we use this equation right here, which says that our change in momentum is our impulse, and that equals our force times the change in time, but the force and the momentum are both vectors, so directions matter, times change in time. We have our change in time. We need to calculate our change in momentum and solve for the force. And that ends up giving us force equals change in momentum over change in time. Right? So we need our change in momentum, and we plug in our change in time to calculate the force. Well, momentum is mass times velocity, and so we take our final mass times final velocity. Mass doesn't change, but the velocity final is what? That's 0, right? So that's our final, and then we subtract off the initial, which is the mass times the velocity initial, whatever that number is. But remember, the negative sign goes with that. So you got to keep that negative sign. And then we divide that by the delta t, which is 2.2 seconds. So all you got to do is take your negative times the mass times the initial velocity, divide it by 2.2 seconds, and you'll get the force that you need. Oh, yeah, that'll give you the wrong sign. Yep. That's quite important since momentum is a vector. The way that you do your subtractions and things, we're not squaring it, so it's not, those negative signs are not going to go away. They're important. Oh, for you two that came to the meeting, did I give you guys t-shirts? I didn't, did I?
I didn't get one.
You did get one, Leslie?
I
So you
didn't
did
get
get one. So the question is, well, let me go get you a t-shirt so you know.
Okay. You have one that's an extra large?
Yeah, that's all I had.
Okay, that works.
However, I think I'm going to make a new t-shirt for the eclipse. I can't decide which one though. There's a really funny one that has a picture of the eclipse and says, and then it would say, "I got mooned in Nebraska."
Oh, that'd be fun.
But I'm not sure how the college would appreciate that. I don't know. I think I might do it anyway without asking.
Well- Well, you could put the school appropriate or something, something like that.
No, I think I'm just going to put I got mooned in Nebraska, and then the Great American Eclipse or something across the bottom, and then the STEM Club logo on the back. And I can make these shirts for like $7 a piece, 50 shirts for $350. Sell them for like 15 or 20, make some money for the STEM Club. I think I could sell 50 shirts like that. I'm pretty sure I could. Yes, Cassidy?
I'm going to be gone. Well, it doesn't matter. Like, I'll be back for class on Monday, but I'm going to be gone on vacation starting
Sorry, during when?
like tomorrow through Sunday.
Okay.
I'm gonna bring my laptop with me and try and do some homework on the way there.
Okay. Will you have an internet connection?
I can use I have unlimited data, so I can use a hotspot.
Okay.
And
Sure.
I was wondering if maybe you could extend the chapter 8 to Monday. So, because I'll get home like Sunday late, and so if I do still have some problems left, I could do them on Monday,
What does it go to? I don't remember when I...
Saturday, which is I'm usually fine with.
Okay.
also, whenever everyone's done with class or whatever, I have some questions on chapter 7 that I wanted to talk to you about.
Let's see here. Calendar. Homework. Oh yeah, homework 7 is due today, right? Homework 8 is Saturday right now. Let's make homework 8. Well,
And I can ask on Monday if I have any questions that.
So do we
okay.
close this?
Hello. Are you here for? We got somebody piggybacking on our class. I don't know why, but we do.
Huh?
Hello, are you supposed to be using this channel right now? Have I gone over into your time?
I think we just need to, we've been here.
Hello, this is Jared Daly. I'm teaching a physics class at the moment. Do you need to use this Zoom account? Well, Cassidy, why don't you go ahead and ask your questions? I'm just going to assume that
They left.
yeah. I need to make the college give me my own Zoom account, or maybe just make my own Zoom account. I don't know.
She said he can hear us.
Yes, I can hear you. I know all, see all. Okay, so Cassidy, tell me what you need for chapter 7.
Okay, I'll start with number 9
Okay.
because the only thing we're given is the distance and that it's supposed to be 100% efficiency.
So when you assume 100% efficiency, that means you're not going to lose any energy in the conversion from gravitational potential energy to kinetic energy, which really just means that your potential energy at the top of the hill has to equal your kinetic energy at the bottom of the hill, and that's the equation you need to solve. Does that make sense?
Oh, maybe I mistyped. Because I did that. Oh no, it's so wrong. So when you just take that 116 times 9, or whatever the number is, times 9.8.
Well, this is how it looks here in the end. Let me get on the whiteboard here really quick. So we're at the top of our hill, and then we're going to be at the bottom of our hill. The height of our hill is whatever height h it is, right?
Right.
And and at the top you're not moving at all, and then you're just going to roll down the hill. So your velocity initially is 0, and your height initially is h. But at the bottom, your height is 0, and your velocity is at a maximum, right?
Right.
And the equation says that all the energy added at the beginning has to equal all the energy added up at the end. And all the energy at the beginning is, we have a kinetic energy at the beginning, which ends up being 0 because our velocity is 0. Excuse me. So our initial kinetic energy is 0 because we're not moving at the top. Then we add that to our potential energy at the top, which is m times g times h. And then our kinetic energy at the end, which is 1/2 mv squared final. mv final squared, there we go. And our potential energy at the end, which is 0, because our height is 0 at the end, right? So we end up solving this equation right here, for V, final. The m's cancel out because there's one on each side. And then you end up solving this equation. GH equals V final squared over 2. So if I multiply both sides by 2, and then take the square root of both sides, that's my equation right there.
Okay.
Just
That
a
1/2
second.
mv squared is that kinetic energy equation, right?
That's correct. 1/2 mv squared is kinetic energy. The
And
mgh is the potential energy.
Okay.
So there's potential energy at the top. The kinetic energy is 0 at the top, and at the bottom there's kinetic energy, and the potential energy is 0 at the bottom.
Right. Okay. Okay, that makes sense. Number 2.
Number 2.
Yeah. I was having problems specifically with the work done by force of tension.
Yep. So
Sorry, you can go, because I didn't know where to start. I tried to run some numbers, but I wasn't sure.
okay, so with this problem, it says they're moving at a constant velocity, which means if you're at a constant velocity, is there any acceleration?
No.
So if there's no acceleration, is there any force?
No.
No. So all the forces acting on this person are canceling each other out. And that's the key to this problem. So let's go ahead and let's see, where'd my drawing go? I can't find my whiteboard. Well, there it is. Okay. So in this problem, we have our slope. We have our person who I'm going to represent with a box. He's alive, not in a coffin. But we have our weight of the person, which goes straight down, and we have this angle. I can't remember what the angle looks like. The angle's at the bottom of the slope here. So we have this angle here at the bottom of this slope, which is theta, right? This is our weight going down here. And then we have a tension that moves up this way parallel. And we have, do we have friction?
Yes.
We have friction. And they're lowering him down the slope, right?
Yes.
So the friction is actually going to point upward because the movement is downward, right?
Yes.
So we have friction upward, we have tension upward, and we have weight downward, right?
Yes.
And the normal force that is perpendicular is this way. We have tension this way. And we probably want to set this up so that we're going parallel and perpendicular to the surface, so that we simplify our lives a little bit. So here's my parallel direction to the surface, and here's my perpendicular direction to the surface, which means I want to break my this weight force into components that are parallel and perpendicular. One of them is going to be perpendicular like that, and one of them is going to be parallel like this, right?
Yeah.
And then this angle, being the big angle, is going to be this angle right here, this theta. This angle and this angle are going to be the same. They're both the big angle and they're triangles, right?
Right.
And then the thing that I want to know, the equations that I'm going to set up are going to be the, let's see, I think they're trying to use this.
Well, you know that the normal force is going to be 0 because it's not doing any work.
Yeah, the normal force is just going to cancel out. So we're just going to deal with the forces that are parallel, right? So we're going to deal with parallel forces here. And we're going to have tension force, which is going to be positive. We're going to have friction force, which is positive. We add those together. And then we have a weight that is parallel, this weight parallel force here, which is going to downward, so it's negative, so it's minus weight parallel. And then that's all the forces in the parallel direction, right? And since there are no forces, those have to all add up to be what?
0.
Right. The tension force is just what it is. The friction force is something. Do they tell us what the friction force is?
Yeah, I guess the kinetic.
It gives us the coefficient, kinetic coefficient of friction. That means we have to calculate the normal force. We'll need that because we'll need that for that equation. And then it has the weight perpendicular, which is easy. So for this equation, we're going to have tension plus the normal force, which is equal to the weight perpendicular. So we'll need that weight perpendicular. And that has to be multiplied by mu static, or mu kinetic rather. And then we subtract off the weight parallel, and that has to equal 0. Well, then we have tension plus weight perpendicular. That's this one right here. Weight perpendicular is next to the angle, so that's going to be our weight times the cosine of the angle theta times mu k. Right? And then we subtract off the weight parallel, which is opposite the angle. So that's going to be weight times sine theta. And then that has to equal 0. And what do they want you to calculate? They want you to calculate the tension.
Well, it's asking for the work done by each of the forces.
Oh, that's the, okay. So do we know the tension? We have to calculate the tension.
You have to calculate it. So my question with that is, do you just calculate the normal tension, or do you do the work, or, like, I don't understand how to connect the two, the work done by tension.
So you have to calculate all of the, what you have to do is you have to calculate the work done by all of these forces combined, right?
Oh.
Well, not by all these forces combined, by each of these forces actually separately. They want them each separately, right?
Yeah.
So you'll use this equation here to solve, because you know mu sub k, and you know w, and you know theta, you can solve this equation for t. And then you'll get t equals some number. Then you can use that t in the work equation. Work equals force times distance, so it'll be t times the distance that they lower them down. Do they tell you how far they lower it down?
Yeah.
Okay.
56.
So then you'll use this equation to solve for t, and then the work done by t will be t times the distance lowered. Then
And then times the, is it going to be cosine in this situation?
do they tell you the distance along the cliff, or do they tell you the distance along the vertical?
Along the line.
Let's see, what do they say?
So along.
Yeah, along the incline, then you just use the distance, because the distance and the tension are in the same direction. And then this is also going to be a negative. There's going to be a negative sign in here because you're pulling up, but you're lowering down, right? So the distance is going to have a negative sign on it. So this distance is going to be like a negative d. So this will end up having a negative involved. The work will be negative. For the work done by friction, it'll be the same thing, except you'll put in the frictional force, which is this thing right here. This is your frictional force. So you'll put in your frictional force times d, and it'll also have the negative sign, because it's in the same direction, right? But then the work done by the gravity, work done by the weight, right, is going to be the weight force, which is this one, times distance. And that one will be positive. It'll be W sine theta, and it will be positive, times D. Does that make sense?
Forgot what I was going to ask. Oh, so with the friction, we have to calculate normal force, which is just mass times gravity, or weight times gravity.
Well, no. Remember that the normal force is only weight times gravity if you're on a horizontal platform. On this angle, the normal force is equal but opposite to the perpendicular weight, which is why we put the perpendicular weight right here instead of the normal force. This is the normal force right here. Weight times the cosine of theta is the normal force.
So the only time normal force is weight times gravity is when it's on a horizontal.
That's right, because when you're on a horizontal thing, like a box like this, then the normal force is directly opposite the weight. Right? Like that. So they cancel out like that. When it's on an incline, it's not in the direct opposite direction as the weight, it's off angle. So only one component of the weight is the normal force.
All right, then I should be good on that. And it makes sense. So just once you find tension, then you're able to plug in everything else and find the work done by E.
Yes. Technically in the way that I did it, I found the normal force to be equal to the weight times cosine of theta first, and then I plugged it into this equation to get tension. But if you follow this line of reasoning, it will work out for you.
One more. Number 4. It had a lot of parts to it, but
Okay, so this one is the projectile launched by the spring at the bottom of a vertical pipe. The projectile is a piece of wood with this good. Spring is compressed 4.2 centimeters. How much potential energy is stored in the spring? So this is all about spring potential energy and changing it to kinetic energy, right?
yeah, so I know how to calculate the spring, the potential spring energy.
Yep.
But is your work by the spring going to be different than the potential?
So work done by a spring is going to be equal to the potential energy stored in the spring.
And then it says in C, it says the spring is released and returns to its original length.
Yep.
And then it put in process, it put the force on it. So like, I just don't understand. Is the work going to be different when it does that, when it's released?
When the spring is released and returns to its original length, in the process it puts a force on the projectile. How much work did the spring do on the projectile? The amount of work it does if it returns to its original length will be equal to the amount of energy that was stored in its potential energy when it was compressed. So B and C really should be equal, like you were asking.
And so A, B, and C would be equal?
Well, they'll all have the same value, but they may be different signs.
Direction.
Yeah, because it's not direction. Remember that the sign when it comes to energy depends on whether the energy is being put into the system you're talking about or being taken out of the system. So in part A, for example, it says the spring is being compressed. How much potential energy is stored in the spring? Then that's a positive number because that's energy you're putting into the spring. So that's energy added to the spring, so that's positive.
And when it's released, it's negative?
And then it says how much work is done by the spring. When work is being done by something on something else, then that is the work that's being done by something and makes something move in the direction that it's forcing is positive as well. So it's all in how they word it. You just have to think is what system are they talking about and is the energy going into it or out of it? And when something is doing work on something else and the energy is leaving the thing that's doing the work, then that is actually positive work being done on something else. So it's a little confusing. Like I mentioned several times, dealing with signs with energy is very confusing. If you don't get it right the first time, you might just try change it by a negative sign and see if it works that way, because you may have just understood it incorrectly. If I look at the, let's see here, 4.2, I don't have a, I'm going to do a quick calculation and see if I can get the sign right. So it's compressed 4.2 centimeters and a half. Times 0.042 times 180. That's 1/2 kx. So I'm going to say that this is 0.159. Got that right. How much work is done by the spring? 0.159. So I think that they wanted that one to be negative. I'm just checking to see if negative signs are the issue. They are, yeah. It returns to its original length, process force on the projectile. How much work did the spring do on the projectile? So that's work done on the projectile is energy going into the projectile. So I'm going to go back to positive with this one.
So it's just trying to show you that it matters how the energy is being used.
That's correct. So the change in kinetic energy would also be 0.159 because it's going into it, it's increasing its energy. So yeah. Then you got to calculate velocity and everything else.
Well, that's all I have.
That's it? Okay.
I sent you the scans with my
Yes, I got those.
tape. And I have the stuff all packed up in the box, and I'll give it to you next week when I see you.
Sounds good.
Thank you.
Thank you. We'll see you later, Cassidy.
Have a great day.
You too. Okay, now I can. Yeah. I'm just going to end that meeting really quick so those people don't try to jump into my meeting again.
That was a little strange. They looked really confused.
Yeah, I'm sure they were. I need to get my own Zoom account that's only used for physics and engineering in my classes, but we'll figure that out later. Okay, so we're back in chapter 8.
Yes, please. So numbers 3 and 4.
And Packer,
Yeah.
a couple weeks ago, or last week when you weren't here last week or the week before because of scout camp and everything. But anyway, we made a decision that we were going to travel to Broken Bow next Wednesday. I don't remember if I told you that. But we're going to go to Broken Bow next Wednesday. So if you can, try to get out a little early from work and we'll leave from here. Sound good? Probably we'll leave, let's see, class starts at 3:30? Yeah, so class starts at 3:30. We'll try to get there by 3, so we'll probably leave here at 1:30 or so. 1:30, but no later than 2. So if you could get out at 1:30, that would be great. If not, we'll try to leave as quickly as possible before 2. Before 2? Okay, well, you just try to get out as early as possible and we'll leave as soon as you can get here. All right, 125 gram baseball pitched. Afterwards, it has a speed of 29 meters per second. What's the impulse of the bat on the ball? So immediately afterwards, they're talking about it being hit, right?
Yep. So what I did was I said, okay, so you change in momentum would equal the final momentum minus the initial momentum.
Now remember, momentum has direction.
Yep.
So which direction is pitching? We'll call that positive. That means hitting would be negative, right?
That's,
And that's going to change your answer probably.
yeah. That was probably where I threw it off.
So it's going to be a much bigger change in momentum because it changes direction.
No, it's still, I tried changing the answer to positive after I got it down to negative.
So that your final momentum is negative, it'll be negative 29 meters per second is the bat hitting the ball, times the mass of the ball. Then I'm going to subtract off the initial one, which was positive, which was 44 meters per second.
Yeah.
Times the mass of the ball, right? So it's minus a positive. So this is going to be minus 73 meters per second times the mass of the ball. Is the change in momentum.
Okay, because
And they don't want the negative, but you still have to use the negative when you're calculating it. They don't care about what direction it is. They just said the magnitude. But you still have to use the negative in the equation to get the right magnitude.
okay. Because so the final one I have.
And you have to convert grams to kilograms, of course.
Yeah, mine shows as 130 grams, so it'll be 1.3 kilograms. Or
No,
0.13.
0.13.
Yeah, sorry, I missed it.
Then multiply that by the sum of the two speeds, essentially. That's what it comes down to.
I'm confused. When the timing zeros and it says immediately after.
For which one?
The difference in time, it says immediately after.
Okay, so since they said what is the magnitude of the impulse the bat put on the ball, then you have to assume that the bat hit the ball, and that's what they're talking about immediately after. So they're not. We're not going to. They didn't tell us the time, but they did tell us the initial and final velocity, which means we can calculate the initial and final momentum, which means we can calculate the change in momentum, which is equal to the impulse. Because impulse is delta p, which is change in impulse. So there's two ways to calculate the impulse. You can either calculate it by the force and the time, or you can calculate it by the change in momentum. In this case, we're going to calculate it by the change in momentum.
And that's what I did when I put it in the positive and negative. It came up wrong both times for my first answer.
Let me
And the first answer being correct.
Mine is 73. 25. It works for mine. All I did was add the 29 and the 44 and multiplied by the 0.125.
So add the 29 and the 44?
Well, it's the same thing, right? If you have a negative for one of them and then you subtract the other one, you get, it's like adding them, right? Except with a negative sign in front. Since they're changing, since it changes direction, your change in speed or your change in velocity
Yeah, I see what I did just now.
is actually just the sum of the two numbers with a negative or a positive, depending on which way is negative or positive. Then you can use the time to calculate the force. If you divide this change in momentum by the time, you will actually get the force.
So, okay, so I got a negative number for the change in momentum, right?
Yep.
So why did you put yours in as positive?
Because they only wanted the magnitude. They're only asking for the magnitude. They don't want to know the direction. You have to use the negative in the equation to get the right number out. But you don't have to tell them the negative or the positive because they don't care. Because everybody's home plate is pointing a different direction. Right? 39.67 newtons. This is just not. Moving all that fast. $230 milliseconds. There's no way that it's spending that much time on it. That's way too long of a time. I would accept 10 milliseconds. 230 milliseconds, you have a reaction time faster than that. A reaction time for human beings is close to that. That's almost a quarter of a second. That's really long time.
Number 4 then, I'm guessing I'm maybe similar error. Possibly.
An impulse burn, so it tells you the 15 Newton seconds is the change in momentum or impulse. They tell you the time.
So what I did was I said if it's, you take the impulse and however long it burns for, right? And that would be your change in momentum, right?
So this is the equation for impulse. And of course, change in momentum is mass times velocity final minus mass times velocity initial, right? And what do they tell us? They tell us mass. Good. They tell us impulse, so they tell us this. And they tell us the initial velocity is 0, right? So it's just mass times final velocity equals impulse. And we know this and we know this. We can calculate final velocity.
So does the time matter at all?
Nope.
Okay.
If they ask for the force, it would matter. But they don't. They ask for velocity. It doesn't matter. Any other questions? We've gone a little overtime, so if anybody needs to leave.
And it doesn't interfere with your schedule at all, staying a little later, though. So I would want to be keeping you from something.
I don't know, actually. It's a good question. Oh, emails.
Where are you with
Oh, your quiz? Just drop it up here on the desk. Now, before we go any further in this summer, we need to meet for the calculus class.
Yes.
I just got an email from Peggy Fisher, who will get you into that class officially, so you won't have to deal with it anymore.
Awesome.
Apparently, it got onto her radar, and she'll take care of things. She's always good at that. But yeah. Anyway.
did you have a specific time in mind? You want to set a meeting for that?
Friday, July. We could meet whenever works. Tuesdays after this class we could meet, for example. We just need to meet once to get you started, and then you can just ask questions about that class whenever you need to.
Okay,
So-
so you're thinking next Tuesday?
Well, let's talk next Monday, actually, just so we don't forget it. I don't know where everybody is. They might be at the pool.
That's what I have,
Okay. Let's see here. I'm going to put something in my calendar so we don't forget. We got to get you guys started on that.
So just meeting next Tuesday, we'll talk about it Monday.
Yeah. We'll talk Monday. I'll put it in my calendar here.
Yeah, that'll work just fine. The only thing that might have interfered with the worship practice in that church, but I'm not on the schedule for this, for the week after. Not that. Wait a minute. How long will we be meeting for?
On Monday?
On Monday or Tuesday?
On Monday, we'll just meet just to show you what to do with your homework and explain a few different things about it. Maybe half an hour.
Okay.
Not long.
So
no.
Monday after class?
Yeah.
Okay. Here's my quiz.
Thank you.
Sorry, I got a little crinkled.
No worries. All right.
Sounds good. Thank you, Mr. Bailey.
Indeed, no problem.
Joe,
Yeah. Welcome. Lots of good times.